Hello and welcome to Sleepy Science. I'm so glad you're here. Whether your day ran long or you simply love drifting off to quiet wonder, tonight we'll float along the softer edges of knowing and peek at a layer of reality your senses can't quite detect. We'll notice how your head ages a whisper faster than your feet, how a teaspoon of a neutron star would outweigh a mountain, and how trillions of neutrinos pass through you this very second like gentle rain you cannot feel. We'll let electrons hum as standing waves instead of tiny planets, sit with the unsettling truth that there is no universal now, and watch change itself, pause under our gaze. We'll see objects lock to invisible tracks as if held by air, feel two empty plates tug together, and hear how your brain quietly predicts the world before you perceive it. So the present is always a hair late. We'll smile at the thought that every shuffle of cards you've ever made was likely unique in all of history, drift with sails pushed by light, and rest in the calm honesty of randomness that hides no pattern. We'll glow faintly with biophotons, admit that bananas and people are softly radioactive, and notice that erasing information releases heat while most of your mass is swirling gluon energy rather than things. We'll let particles become ripples on fields. Remember that you share atoms with everyone who ever lived, and follow plants as they borrow quantum tricks to move sunlight with grace. We'll listen to hot and cold water sound different, allow space to expand faster than light without breaking causality, and slow atoms with beams until they barely move at all. We'll feel the staggering space of chess games outnumber atoms, catch cosmic rays on a phone camera, and step into laboratories colder than the vacuum between stars. We'll hear black holes ring like struck bells, notice Earth's core spinning at its own pace, and end with a mirror that can hush phantom pain. Before we begin, I'd love to know where you're listening from and what time it is, wrapped in a blanket under quiet stars, or letting the day soften under warm indoor light. If these calm explorations help you rest, please like the video and tap subscribe. It gently helps more sleepy minds find their way here. Now take a slow breath. Feel the bed hold you, and let's begin our quiet drift. Your head ages faster than your feet. Raise your eyebrows and you've just cheated time. The tiny lift puts your head farther from Earth's center, and for as long as it stays higher, it ages a touch faster than your feet. That sounds like a late-night brain teaser, but it's a measured fact of nature that came from a radical idea. Gravity doesn't only pull on things, it bends time itself. You live inside that bending every day without noticing. General relativity says the stronger the gravity, the slower time flows. And because gravity is a hair stronger near the ground than a little higher up, the clock close to your shoes ticks ever so slightly slower than the one near your scalp. You don't feel your minutes stretching or shrinking. The effect is unimaginably small over a meter or so, but the universe keeps the books accurately, and the books say your head gets the extra moments. Physicists didn't leave this as philosophy. They watched it happen with exquisitely stable atomic clocks that count light's rhythm inside trapped atoms. Raise one clock by just a few centimeters, and it gains on its twin below. Stretch that separation to your full height, and the difference becomes clearer in the math. Over an entire human lifetime, assuming you spent much of it upright, the head can pull ahead by on the order of hundreds of nanoseconds, fractions of a microsecond, still tiny, but emphatically not zero. If that sounds like trivia, think about the machines that rely on it. The satellites guiding your phone's maps orbit far above the ground in weaker gravity and zip around quickly. Both altitude and speed tweak their ticking. Engineers correct for those shifts, because if they didn't, your location would drift by kilometers each day. In a world that depends on timing, time's humility matters. Even skyscrapers feel it. A clock on the top floor runs faster than one in the basement. Underground laboratories, mountain observatories, long airplane flights, all experience time just a little differently. You can imagine your own day as a slow dance with these differences. When you sleep flat, your whole body shares nearly the same gravitational potential. When you stand, you stretch across a faint gradient. None of this changes your birthday or steals your memories. It simply reminds you that now isn't perfectly universal. The present is local, woven from where you are and how you move. There is a quiet beauty here, Reality is not a rigid stage, but a responsive fabric, and you are stitched into it in a way that makes your height, your hikes, even the floors you visit part of your personal timeline. If you want a concrete mental picture, imagine two nearly identical songs playing on two speakers at slightly different volumes. The melody is the same, but one is imperceptibly ahead by a fraction of a beat after a very long time. That's your head and your feet, sharing one body, yet accruing time differently because the Earth's mass warps the score. It's tempting to ask whether you can hack this, live upstairs to gain more life, but nature is not fooled. The gains are so small that moving house won't grant you extra years, and there are trade-offs. Motion slows your clock compared to rest, so training runs and long flights very slightly tilt the balance the other way. The point isn't bio-optimizing the clock, it's understanding the clock at all. The lesson is that everyday life sits inside curved space-time, and what feels steady is actually subtly elastic. When scientists first proposed this, it was bold and strange. Then came hard evidence. Photons climbing out of Earth's gravity shift in energy, an effect actually measured in the last century. Later, portable atomic clocks were flown on airplanes and then compared with clocks that stayed at home. The airborne clocks disagreed by just the amounts predicted once you add both speed and altitude. Today, timekeeping has become so sharp that simply moving a lab instrument up a shelf reveals gravity's fingerprint, and geophysicists can even use this sensitivity to map variations in Earth's mass below. If all this leaves you with a soft unease, how can reality be so flexible? Notice what it invites you to do, to replace a single, absolute now with a more generous picture. Your experience is already a kind of local story. The physics just confirms it. You are never fully detached from where you are. The ground under you, the buildings you climb, the hills you wander, the sky you fly through, each writes minuscule edits into your personal chronology. That recognition doesn't make life heavier, it makes it more intimate. Instead of a cold universe, you find a precise one that pays attention to context. And context is what your choices are made of. Think of patience differently the next time. You wait for an elevator. Time itself is not evenly poured, it's ladled by gravity. Think of perspective differently the next time you argue online. What feels perfectly simultaneous to you may not be, even in principle, to someone moving differently or sitting elsewhere. Think of wonder differently the next time your navigation app snaps you to a street with uncanny accuracy. There are hidden corrections humming in the background so your tiny blue dot knows where it is on a turning planet. Most of all, think of yourself as gently coupled to the cosmos. You are not floating in a neutral void. You're on a world that slows and loosens time by tiny amounts from ground to ceiling. Your body is a ruler across that gradient. Your life is long enough to add up those fractions into something measurable, even if not meaningful for aging creams or life hacks. The meaning is in the comprehension. Once you know that time can change simply because of where you stand, you can look at ordinary moments with physicists' eyes and poets' calm. Stand tall, sit down, climb stairs, lie back. The universe will keep conducting its careful experiment through you. And when you close your eyes tonight, you can smile at the quiet absurdity that was never absurd at all. Today your head lived a whisper more than your feet, and the difference, too small to feel, big enough to prove, makes the everyday floor beneath you part of the machinery of time. A teaspoon of neutron-star weighs a mountain. Imagine tipping a teaspoon into the heart of a dead star and lifting it toward the light. If you could somehow keep it from exploding, that tiny scoop would carry the mass of a mountain in your hand. A neutron star is what's left after a massive sun exhausts its fuel. Its core collapses, and matter is crushed to densities that sound like fiction, but are measured across the sky. The whole star may pack more mass than our sun into a sphere roughly the width of a city, and inside that pressure cooker, atoms are squeezed past their usual limits so that protons and electrons marry into neutrons. That is why the spoonful is so heavy. Not because neutrons are exotic, but because gravity has forced ordinary matter into a configuration where almost every gap is gone, like a library whose books have been pressed until the shelves vanish and page touches page. If you want a mental yardstick, imagine your teaspoon holding about 1 billion tons, close to the mass of a cubic kilometer of ocean water, or hundreds of great pyramids stacked into a thimble's space. But that comparison is only a doorway. The real wonder is how nature built such a thing. When the iron heart of a large star collapses, inward falling layers slam to a halt on a core that suddenly becomes as stiff as nuclear matter, and a shock, plus a wind of ghost-like neutrinos, flings the outer layers into space. That is the supernova you've seen in photos. The remnant left behind is the neutron-star, its surface a crust just a kilometer or two thick where atomic nuclei still cling together in a sea of electrons, beneath which the rules change again. Neutrons seep out, drip, and swim through a lattice so dense that it may organize into whimsical shapes nicknamed pasta, spaghetti-like strands and lasagna-like sheets formed by the quiet tug-of-war between nuclear attraction and electric repulsion. Deeper still, most physicists think the neutrons become a superfluid, able to flow without friction, and a fraction of protons form a superconductor that locks in magnetic fields of terrifying strength. In some neutron stars, those fields are so intense that we give them a special name, magnetars, and their sudden crustquakes can light up space with bursts of high-energy radiation in less than the time it takes you to blink. If your instinct is to ask, could I ever hold that teaspoon? The honest answer nudges you toward what matters. Remove neutron star matter from its crushing gravity, and it won't stay that dense. The same neutrons that were stabilized by pressure would try to expand. Many would decay back into protons and electrons, and the sample would flash outward with catastrophic violence. So the teaspoon thought experiment is a lesson about context. The weight you're picturing is only meaningful within the embrace of the star's gravity, a reminder that matter isn't just what it is, it's also where it is. And the where of a neutron star is extreme in other ways you can grasp without equations. Its surface gravity is so strong that if you could stand on it, which you cannot, your feet would be anchored with a pull hundreds of billions of times stronger than on Earth. The escape speed from that surface is nearly half the speed of light, so anything that leaves must be launched like a bullet from the deepest well the universe allows before the well becomes a black hole. Some neutron stars spin hundreds of times each second, and if their magnetic field is angled just so, beams of radiation sweep through space like lighthouse beams. We call those pulses, and their ticks are so steady that astronomers use them as cosmic clocks to test physics and map the galaxy. Others collide in pairs, spiraling together until they merge with a shudder that shakes space-time itself. We've heard those mergers as ripples detected by gravitational wave observatories, and watched their afterglow as kilonovae, whose light carries the fingerprints of newly forged heavy elements. Gold, platinum, iodine, the stuff in your ring, in your salt, in your body, born in the violence of these tiny suns that died and then met again. So the teaspoon does more than shock your imagination. It points to a chain of origins that runs all the way to you. The path from starlight to spoonful is built from real clues, precise measurements of how pulsar radio pulses slow and glitch, which reveal the superfluid inside, X-ray brightness and pulse shapes that let us estimate a star's size, and thus how tightly matter can be packed before physics breaks, and the way two neutron stars deform each other as they dance, which tells us how stiff their insides are. Each method converges on the same picture. Nature found a way to compress matter to nearly the density of an atomic nucleus, and then to balance it on a knife edge between collapse and explosion. The crust itself might be the strongest material in the universe. Simulations suggest billions of times stronger than steel, capable of holding mountains only centimeters high against that crushing gravity. Even the air above the surface is hardly air at all, more like a film a few centimeters thick of superheated particles and light. If these facts feel like opposites, delicate films and billion-ton teaspoons, it's because the neutron star is an encyclopedia of extremes bound into one object. And the practical mind might ask, what is this good for? Beyond satisfying curiosity, these stars are laboratories that let you test ideas no machine on Earth can reach. They show you how matter behaves when the gap between particles disappears, how magnetism behaves when it can sculpt light, how rotation behaves when friction is not a thing, and vortices in a superfluid pin and unpin, sending a star into sudden hiccups we can measure from halfway across the galaxy. They teach you that solid and fluid are not simple categories. that pressure can rewrite the identity of matter, that the periodic table is a travel diary, not just a list. Most of all, they train a habit of mind. The next time you stir sugar into tea, let the spoon become a scale of wonder instead of weight. Picture the absurdity of 1 billion tons poised on a silver oval, and let that image whisper what science keeps finding. That reality often hides its most important truths behind numbers that look impossible until you understand the story around them. You don't need symbols to carry that home. You need a question. What else in your life looks ordinary because you've only ever seen it at human pressure? The neutron-star's teaspoon answers by example. Change the conditions and matter reveals a second self. Out there, in the remnants of exploded suns, gravity and quantum rules collaborate to press the universe's pages together. In here, in your kitchen, the pages are loose and friendly. The contrast is not meant to scare you. It's meant to give you a steadier awe. Somewhere tonight, a lighthouse star is sweeping a beam through dust. The crust beneath it is humming with tension, and your world, soft, open, breathable, rests at a pressure that lets tea be tea and a spoon be light in your fingers. Knowing that, you don't just marvel at a mountain in a teaspoon, you learn to read the conditions that make things what they are. And that is the kind of knowledge that stays when the showy numbers fade. Trillions of neutrinos pass through you every second. A ghost wind is pouring through you right now, silent and unstoppable. And if you could hold out your hand to catch it, you'd still feel nothing. Yet every second, trillions of tiny travelers pass through your skin, your bones, your heart, and keep going as if your body were mostly empty space. They are neutrinos, uncharged slivers of matter born in the hottest, most secret places in the universe. And the only reason you haven't heard them knocking is that they almost never touch anything at all. Start with the nearest forge. The sun's core fuses hydrogen into helium, and in the process releases a flood of neutrinos that stream outward at nearly the speed of light, escaping in seconds from regions where light itself takes tens of thousands of years to wriggle free. By the time that flood reaches Earth, tens of billions of neutrinos are crossing each square centimeter of your body every second, and that's just the daytime drizzle from our own star. Add to that the steady background from radioactive elements inside the planet, the breath of distant supernovae long faded from view, the faint whisper of cosmic rays striking the atmosphere, and the signature of human-built reactors. And you start to see why the word trillions is not poetic flourish, but a conservative count. The puzzle is interaction. Neutrinos ignore electric charge and mostly shrug off the strong nuclear grip. So they meet the world through the weakest link in nature's chain, which means they can cruise through a wall of lead so thick you could stack it to the stars and still not be sure you'd stop them. A rough way people put it is that you'd need a wall of lead about a light year thick to cut a beam in half. How do you study a particle that acts like a rumor? You give it silence and watch for a flicker. That's why some of the most haunting observatories on Earth are buried deep underground or frozen into Antarctic ice. Vast pools of ultra-clear water or cubic kilometers of glassed-in ice, lined with sensors, waiting for the rare moment when a neutrino finally glances off an atomic nucleus and kicks out a charged particle that outruns light in that medium, painting a cone of blue, Cherenkov light, so brief and faint that it would be lost in daylight, but becomes a crisp signature in the dark. These detectors have turned neutrinos from theory into a working language. When a star collapses into a supernova, neutrinos burst outward first. In 1987, a handful of neutrinos arrived on Earth from a dying star in a neighboring galaxy before the visible light reached our telescopes. A quiet early warning that confirmed our picture of what happens in the heart of a stellar explosion. When researchers counted neutrinos from the Sun in the late 20th century, they found too few compared to the solar furnace we understand so well. The mismatch wasn't a failure of the Sun, but a clue about neutrinos themselves. They change identity in flight. There are 3 kinds, and as they travel, they can morph from one to another, a behavior that only makes sense if neutrinos have mass, however tiny. The discovery of this shapeshifting solved the missing neutrinos and forced physics to admit that the simplest picture of mass was incomplete. That small correction has big consequences, because neutrinos hardly interact and barely notice magnetic fields. They fly in straight lines from their sources, turning neutrino astronomy into a way to look directly into places that fog light or bend it beyond recognition. When a detector at the South Pole traced a single, exceptionally energetic neutrino back to a flaring galaxy billions of light years away. It showed that we can pinpoint violent engines at the edge of the visible universe, using messengers that thread the chaos untouched. Closer to home, scientists now measure geoneutrinos from radioactive decay inside Earth, using them to estimate how much of the planet's internal heat is still powered by natural radioactivity. Others watch antineutrinos from nuclear reactors as a non-invasive monitor that can reveal whether a reactor is running and how it's burning fuel without crossing the fence. And in the future, as detectors grow in cleverness, we may use neutrinos to take crude scans of Earth's interior, revealing density contrasts the way a doctor uses X-rays. Except our source is the cosmos itself. Even the universe's baby picture may be written in a neutrino script. Just as there's a relic glow of microwaves from the hot, early universe, there should be a colder sea of ancient neutrinos left over from the first seconds after the Big Bang. A background so gentle we haven't yet tasted it directly, but so real that it already tugs on the growth of galaxies in ways we can measure. If you're wondering whether all this rests on fragile assumptions, look at the mesh of evidence. The day-night difference in solar neutrino counts as particles pass through Earth on the long way to a detector. The seasonal rhythm caused by our orbit. The sharp, ring-like light patterns in water tanks that reveal the flavor of the neutrino that sparked them. The crisp timing of reactor turnarounds mirrored in antineutrino rates. The gravitational wave alerts of colliding neutron stars followed by neutrino hunts to complete the story. And the global early warning networks that will watch for the next supernova by listening for neutrinos first. There are still open questions that keep the field honest. We've measured differences between neutrino masses, but not the absolute scale. We're still learning the ordering of those masses, and we do not yet know whether a neutrino is its own antimatter twin, a subtle identity question with consequences for why the cosmos has more matter than antimatter at all. But none of those unknowns erase what is already firm. You live in a constant storm of particles that treat you as transparent, and by catching a few sparks of their passing, we have learned to read the sun's core in real time, to time the death throes of stars, to audit our own machines, and to glimpse physics that doesn't show itself any other way. So the next time you feel alone in a quiet room, remember that you are anything but, every second. A river of neutrinos threads your body without a sound, and in a world full of loud claims, there is something deeply grounding about truths that don't announce themselves. They just keep moving, indifferent to walls and arguments, waiting for the rare moment when we meet them with the right kind of darkness, patience, and a sensor sensitive enough to see a blue whisper in the night. Electrons don't orbit. They're standing waves. Stop picturing electrons as tiny planets and start listening for a note. What you call an electron in an atom is more like a standing wave humming around the nucleus, a pattern that holds its shape the way a plucked guitar string settles into stable ripples. And once you let that image in, a lot of stubborn mysteries begin to make gentle sense. If an electron were a little ball circling a charged center, it would constantly radiate away energy like a camera drone that can't stop shedding battery, spiraling inward and crashing in an instant, which obviously doesn't happen. Atoms are stable. Your body and the air and the stars don't vanish, so nature must be using a different rule. The electron isn't orbiting, it's resonating. Standing waves only survive when they fit the space they live in, when crests and troughs line up with themselves in perfect rhythm. And that fit enforces allowed shapes and energies around the nucleus. Anywhere the pattern can't consistently fold back on itself, the wave cancels, leaving nodes, quiet regions where the electron will not be found. Those shapes are the orbitals you've seen sketched as spheres, dumbbells, clover leaves, and elegant hybrids. Not because some artist took liberties, but because the standing wave has that geometry baked in. The simplest S orbital is a hush that swells evenly in all directions. A p orbital is like a two-lobed breath with a nodal plane in the middle, and higher ones bloom into more petals and rings, each with its own pattern of bright probability and silent no-go zones. This way of seeing does more than rescue atoms from collapse. It explains why they glow with sharp colors, and why chemistry has a pulse. When an electron changes its standing wave pattern, say it drops from a shape with more wiggles to one with fewer, it must shed the difference as a photon whose color matches the energy lost, which is why heated gas from sodium lamps shouts a specific yellow and hydrogen paints a ladder of crisp lines. You're watching a wave reorganize itself and send the leftover rhythm into space as light. It also explains why elements build the world with personalities. Because each nucleus corrals its standing waves with a different pull, orbitals fill in a particular order that sets the table of the elements. And the way those outermost waves overlap between neighboring atoms is the handshake we call a chemical bond. Covalent bonds are two atoms agreeing to share part of a standing wave pattern between them, forming a new combined shape that holds both nuclei. Metallic bonds, by contrast, come from many atoms, allowing their outer waves to spread through the whole crowd, which is why metals conduct and gleam. Their electrons are not caged marbles, but delocalized notes that can flow. This is not hand-waving. We can see the fingerprints on atomically flat metal surfaces. Researchers have nudged individual atoms into rings, the famous quantum corrals, and then watched concentric ripples of electron density appear inside, the unmistakable signature of standing waves reflecting between the walls. In another set of experiments, atoms in a gas were freed with carefully tuned light and guided so that their departing electrons drew pictures on a detector, revealing node and ring patterns that match the predicted shapes from the standing wave story. Closer to everyday scales, the very tips of scanning tunneling microscopes can trace the lumps and hollows of a molecule's electron density, not as a photograph of little balls, but as a map of where the standing wave bulges or fades, evidence that what matters is the pattern, not a path. Once you start to think in patterns, more of the world lines up. The pleasant sting of mint or the heavy sweetness of vanilla is partly about how a molecule's shape and electron clouds dock into receptors. The color of leaves and blood comes from particular gaps between standing wave energies that favor absorbing some wavelengths and reflecting others. The fact that diamond is hard while graphite is soft arises from how carbon's waves connect in 3 dimensions in one case and in flat sheets in the other. Even the way sunlight converts to charge in a solar panel can be told with this language. Electrons in a solid have standing waves that spread across many atoms, and there are bands of allowed energies separated by forbidden regions. A photon of the right energy nudges an electron to a higher band where it can move, and current is just the coordinated motion of many such notes through the lattice. If you're tempted to ask, but is the electron a wave or a particle? You can loosen the grip of that either-or by noticing how your own experience works. When you choose to check where the electron is, you get a location, a dot on a screen, a click in a sensor, a particle-like answer. When you let it evolve without peaking, what travels is a spread-out possibility, a standing wave that can possess shape without position, the way a room can hold a chord without a single point at which the sound lives. That dual behavior isn't a trick. It's a lesson about questions. Ask where and you receive a place. Ask how it resonates and you receive a pattern. The refusal to live as a pinprick is exactly what saves atoms, and by extension, you. It keeps electrons from draining away energy in a doomed spiral and gives them instead an honest compromise. Stability while they keep the same pattern, light only when they change it. You can test this stability in 1,000 ways. Put a gas in a glowing discharge tube and split its light with a prism to see the rail-thin lines of allowed transitions. Hit a crystal with X-rays and read the spacing of its electron standing waves in the diffraction pattern. Cool atoms to near absolute zero and watch their matter waves swell and overlap until whole clouds act like a single coordinated ripple. And there are soft, almost poetic corollaries in daily life. The smell that makes you remember a childhood room, the taste that makes you pause, the shimmer in a beetle's shell, the way soap bubbles throw bands of color across a gray afternoon. All are, in one way or another, the world answering with standing waves to the boundaries it inhabits. Your atoms are playing by the same rule. The lesson to carry is not that electrons are really this or that, but that explanation gets better when you let go of the picture of little planets. In its place, you can hold a more truthful image, a quiet architecture of resonance around tiny centers, a language of nodes and overlaps that writes the pages of chemistry and the colors of your day. And when you close the book tonight, you can do it with a calmer certainty. The stability of matter is not a lucky accident. It is the natural grace of waves that have found a home. And by learning to read their shapes without forcing them into orbits they never had, you give yourself the freedom to see the ordinary as a carefully tuned instrument, always humming, sometimes shining, and, if you listen closely, inviting you to think in patterns rather than paths. There is no universal now in the universe. Try this. Imagine two observatories parked on opposite asteroids, a light year apart, each with a camera shutter set to click at the same time. And imagine you're drifting past in a fast ship, trying to judge whether those clicks were truly simultaneous. You can't, not in any way that every observer would agree on, because in our universe now is not a universal curtain that drops across distant places at once. It is a local slice that depends on how you're moving. That unsettling idea follows from two simple facts that experiments have hammered into certainty. The speed of light in empty space is the same for everyone who measures it carefully, and the laws of physics look the same, no matter how smoothly you're gliding. If light speed is fixed, then clocks in relative motion must disagree not just about how long intervals are, but about which distant events line up to the same present. This is easiest to feel with a story. Picture a long train and a quiet platform. Two lightning bolts hit the front and the back of the train. The person on the platform stands exactly midway and sees the flashes arrive together, so for them the strikes were simultaneous. But someone sitting midway inside the moving train is carried toward one flash and away from the other. Because light speed doesn't change to help them, the flash they're moving toward reaches them first. The traveler swears the strikes were not simultaneous, and both witnesses are right within their own frames. What changed wasn't the bolts. What changed was the slice of time each observer used to compare distant happenings. This is called the relativity of simultaneity, and it is not philosophy fluff. It is baked into how we build and coordinate technologies that depend on precise timing across distance. Radio astronomers, for example, link dishes spread across Earth into one giant instrument by matching timestamps from ultra-stable clocks. To line up the same cosmic wavefront, they correct for the motion of our planet and the motion of each station so that now at station A and now at station B refer to the same slice in the chosen frame. Metrology labs that shuttle time over fiber optic cables between cities must account for the fact that signals sent in opposite directions do not return to the senders. Desk at the same moment for everyone if the endpoints are moving differently. Even inside particle colliders, where detectors wrap around violent collisions, software must sort out the order of sub-events produced by particles zipping close to light speed. The reconstruction only makes sense when you respect that different parts of the apparatus and different analysts may define their comparison slices differently unless a common convention is enforced. The point is not that anything goes. Cause and effect still have a backbone. If one event can send a signal to another without breaking the light speed limit, all observers will agree on their order. Disagreements only happen for pairs of events so far apart and so close in time that no light signal can link them, what physicists call elsewhere. For those pairs, the universe gives you a kind of diplomatic freedom. Observers moving differently will carve up space-time with slightly different now planes and will sort those events in different orders, yet none of them can turn an effect into a cause or send a message to the past. This matters the moment you stretch your imagination beyond the backyard. Suppose you and a friend each head off in different ships at high speed and then try to define when the same birthday happens for both of you next year. The notion dissolves. Each of you can keep a perfect diary that records local seconds, local meals, local sunrises on your instrument panel, and you can later compare notebooks when you reunite. But while you are separated and in relative motion, there is no global calendar page you both stand on at once. We often cheat around this on Earth by adopting convenient standards. Time zones, universal coordinated time, even a cosmic standard tied to the faint afterglow of the early universe, where the average motion of galaxies is at rest. Those are useful choices, not revelations of a universal present. Nature does not hand out a master clock. It hands out a rule for how different clocks relate when they move or sit in different places. And you build your shared now by agreement, like agreeing on which map projection to use for a round planet that won't lie flat without distortion. If this makes you uneasy, how do you live without a global moment? Look closer at how your life already works. Your brain knits its sense of present out of signals that take time to arrive. Light from the room, sound from the hallway, nerve impulses from your skin. It buffers, aligns, and smooths them into a cohesive scene that feels instant. Physics says the world does something similar at grander scales. Each observer knits a present using their own motion as a loom. When you're quiet in a chair, your now slice is almost parallel to that of a neighbor across town. Start moving fast enough and that slice tilts. The tilt is tiny at everyday speeds. which is why this never troubled a farmer or a sailor. But it is real, and sensitive instruments reveal it. A practical lesson falls out. Any project that relies on synchronizing distant devices needs a clear statement of which frame defines simultaneous and needs to bake in the corrections. That's not a nuisance. It's how we keep our pictures honest when we stitch data across horizons. The larger lesson is gentler. You don't inhabit a universe with a single global drumbeat. You inhabit one where rhythm is local and harmony emerges when we agree on how to count. That can change how you think about communication, about patience, and even about disagreement. Sometimes two people can look at the same pair of far-off events and tell different, internally consistent stories about their order, and both can be truthful, because neither can influence the other. The humility here isn't resignation, it's accuracy. It frees you from the instinct to imagine that there must exist a single, absolute schedule pinned somewhere behind the stars. Instead, you can picture history as a loaf cut at many angles, each slice a valid present for someone. You carry one of those knives, choose your cuts carefully, share your conventions, and you will find that even without a universal now, you can build reliable bridges of understanding. And when you lie back tonight and feel the world slow, remember that the calm you feel is yours, local and earned. Somewhere, a spacecraft is racing and its crew's present is tilted with respect to yours. And both stories fit inside the same patient rules. No betrayal of cause and effect. No secret global bell. Only a world that lets many honest clocks sing together without insisting that they strike noon in unison. Quantum Zeno effect. Watching freezes change. What if paying attention could hold time still? Not for a kettle or a traffic light, but for something so small that asking it a question changes what it is. In the quantum world, watching can genuinely slow or even halt a system's natural change. And the idea isn't a poetic exaggeration. It is a measured effect named after Zeno's paradox of an arrow that never seems to move. And you can feel its logic without equations. Left alone, a fragile quantum state will evolve. An excited atom will drop and glow. A particle poised at a barrier will leak through. A delicate superposition will drift into something else. But if you interrupt that evolution with rapid, repeated checks, you keep resetting the system into the very condition you're asking about. Like tapping undo so frequently that no new sentence ever gets written. Start with the simplest picture. An atom excited to a higher energy is inclined to fall and emit light. If you hit it with a quick query, are you still excited? In the form of a brief probing pulse. And you do this again and again faster than the atom's own natural timescale for changing. The probability that it has time to begin the slide between queries collapses. It is found excited yet again and again, and the fall is delayed. This is not about consciousness or human eyes. Any interaction that extracts which state information counts as a look, and in the lab that look can be a laser tickle, a microwave touch, or a tight coupling to a detector that would light up if change occurred. Ion traps were among the first playgrounds where scientists proved the point, holding single ions in place with electric fields, and then peppering them with gentle questions so often that their transitions slowed to a crawl. Ultra-cold atom experiments pushed the idea further by building escape routes, optical lattices and thin barriers, and showing that atoms poised to tunnel would hardly move if you kept peaking, while easing off the peaking let them slip away. Superconducting circuits, the kind that aim to be qubits in future computers, have also shown the effect. By continuously monitoring whether a qubit has flipped, researchers can suppress the flip, pinning the system in a chosen subspace, as if attention had become a fence. Under the hood, the reason this works is that quantum change doesn't look linear at the very beginning. For very short times, the chance that a system has left its initial state grows quadratically, not steadily, and frequent projections back onto the same state keep tossing it to the starting line before that curve truly ramps up. From a control point of view, the move is powerful. Instead of engineering an impossibly perfect isolation from the noisy world, you can sometimes stabilize a state by interacting with it in the right way and at the right cadence, turning measurement from a destroyer into a guardian. Hospitals do not use this trick for patients, and you cannot stare a snowflake into mid-air, but quantum engineers are learning to apply it to information. Error suppression schemes create Zeno subspaces, protected zones where certain kinds of evolution are frozen out because the system is watched along those channels. It's like installing turnstiles that let only the motions you want pass through. The same idea, informs designs for sensors. If you can prevent an unwanted decay but still allow a target interaction to nudge the system, you increase contrast and sensitivity. There's a twist that keeps the story honest. Watching isn't always freezing, done at the wrong rate or with the wrong kind of coupling. Frequent looks can speed change instead, the so-called anti-Zeno effect, by broadening the system's options and giving it more ways to decay or escape. Experiments have seen both sides depending on how probing and environment are tuned, which means this isn't a slogan, but a tool with settings. You can choose to inhibit, to accelerate, or to steer. The practical lesson is that in the quantum lab, the boundary between system and measurement is not a castle wall. It's a valve you can open and close to shape destiny. If that sounds like mysticism, check the receipts. Detectors buried in silence see the telltale pause in decay when interrogation is rapid. Cold atoms corralled by light fail to cross barriers under intense questioning, but begin to flow when the questions relax. Microwave readouts of qubits show fewer flips when monitoring is continuous and aligned with the protected state. Even the mathematics you're sparing yourself today whispers the same plot. What you can't resolve quickly, you can't let evolve freely. For daily life, there's a softer moral that doesn't abuse the physics. Attention in this realm is not about effort or intention, but about information, about coupling a delicate thing to the world and thereby changing its options. You already know a version of this in reverse. Expose a private idea too early to loud feedback and it can stall. Give it a quiet stretch and it grows. The quantum Zeno effect is the precise, testable cousin of that intuition, with stopwatches and photodiodes instead of feelings. It teaches you to ask better questions, slower or faster, depending on whether you mean to let something change or keep it safe. And when you let your eyes close tonight, you can hold a subtler picture of control. Not a grip that squeezes harder, but a rhythm of gentle checks that, at the right tempo, persuade a restless state to stay, and at a different tempo, invite it to move. Proof that even at nature's smallest scales, timing is not just a detail, but the lever that chooses whether a possibility hardens into a fact or lingers, unspent, a moment longer. Quantum locking, objects that levitate and stick to air. Set a coin-sized ceramic puck on a dish. Pour a white fog of liquid nitrogen until it crackles with cold. Then slide a small magnet beneath it, and watch your intuition stagger as the puck lifts, hovers, and, most strangely, locks in mid-air as if someone glued it to an invisible rail. Tip the magnet and the puck tilts with it. Flip the track upside down and the puck hangs there like a bat, stuck to nothing you can see, which is why people call it sticking to air. But the truth is better than magic. You're seeing a superconductor turn magnetism into sculpted pathways and then refuse to let go. The key is that below it's critical. Temperature, a superconductor carries electric current without resistance and reorganizes magnetic fields with a bold rule called the Meissner effect. Rather than letting magnetic lines thread the material, it launches thin surface currents that cancel the field inside, making the superconductor behave like a perfect, restless mirror for magnetism. That alone can make an object float, because the mirror currents push back against the magnet the way two like poles repel. But that simple levitation is skittish, easily nudged off balance. The locking comes from a second, richer rule that some ceramics obey. They are type 2 superconductors, which, under strong fields, allow magnetic lines to pierce them only in narrow, thread-like cores called vortices. Each vortex is a little tube where superconductivity gives way so a sliver of field can slip through, and everywhere else, the material still expels magnetism. Because the currents circled around those tubes are part of the superconductor's quantum order, each vortex carries a fixed, indivisible amount of magnetic flow, and because real materials have tiny imperfections, grain boundaries, defects, pores, those vortices prefer to sit in those anchoring spots, the way a tent stake bites into rough ground. Now slide the ceramic over a patterned magnet, and you write a forest of invisible stakes through the puck. Try to move it, and those pinned vortices drag, tugging the whole piece back into alignment so the puck doesn't just levitate. It remembers a position and orientation with surprising stubbornness. This is why a locked superconductor can ride inches above a magnetic track and cannot be knocked off. Those internal stakes are insisting that the superconductor's internal map of field lines stay registered to the external map, as if two sheets of Velcro had found each other. If you've seen tabletop demos with rails that whip a small superconductor around curves and loops, what guides the path is not air but the track's magnetic topography, often built from repeating arrays of permanent magnets that shape the field into ridges and valleys, and the superconductor wedges itself into that landscape. Move the track, and the valleys move, so the levitating puck follows faithfully, even upside down, because the binding is to field lines, not to gravity's direction. Important honesty check. This is not anti-gravity. Weight is still there. It's just balanced by electromagnetic forces that arise from the superconductor's insistence on maintaining its ordered state. Earnshaw's old theorem once told us you can't get stable levitation with static magnets and ordinary materials. But superconductors dodge that rule because they create their own currents and, with pinned vortices, their own kind of magnetic friction against sliding in the field. They are not passive beads being balanced. They are active, coherent matter shaping the field around them. In practice, the objects that show this trick are usually brittle copper oxide ceramics cooled with liquid nitrogen, which puts their temperature low enough to switch on superconductivity while still being manageable outside a national lab. Their quantum coherence length, the distance over which electrons pair up and act as a single wave, is tiny compared to the scale of the magnet pattern, and their penetration depth, the distance fields can push into them, is just enough to let vortices thread like needles through fabric. You don't have to know those names to feel the upshot. The material has the right blend of expulsion and allowance to both float and lock. You might wonder how far this goes beyond a party piece. Quite far. The same idea of flux pinning underlies quiet, frictionless bearings that can support heavy loads without wear, because the contact is through field lines rather than surfaces. Spinning flywheels can store energy with less loss, and precision stages can glide with uncanny repeatability since nothing rubs. Maglev transportation explores a larger cousin of the effect. Some designs use superconducting coils for lift and guidance. Others use clever arrangements of permanent magnets and induced currents. Either way, the promise is riding on cushions of magnetism that cut rolling resistance to almost nothing. Medical scanners and particle accelerators rely on superconductors for strong, steady magnetic fields. And while those devices don't levitate themselves, they are built on the same refusal to waste energy in resistance, a refusal that ultimately makes levitation possible at all. There are real limits that keep the dream sober. Superconductors stop behaving if you push the field too high, the current too strong, or the temperature too warm, and ceramic types are tough to engineer into large, flexible structures. Even flux pinning can creep slowly as vortices find new anchor points, which means a locked position can wander if you wait long enough. But those practical edges don't dim the lesson the demo offers your intuition. When you see a puck stuck to air, you're meeting the way quantum order spills into the macroscopic world. The electrons move in coordinated pairs that act like one extended entity, and that coherence gives the material leverage over a magnetic environment millions of times larger than the scale of the electrons themselves. It invites you to think of magnetism not as lines drawn in textbooks, but as a real landscape you can shape and inhabit. By patterning a track as a series of ridges and pockets, you can write an invisible road that a superconductor will follow without touching it, carrying a small camera, a sensor, a load, whatever you need, along a path defined entirely by a field. And it asks a more personal question about control. Most of the time you try to grip things by pressing against them. Here, the cleanest control comes from not touching, from respecting an order the material wants to keep, and designing your environment so that its preference does your work. Later, when the fog has cleared and the puck sits quiet again, you can hold on to that softer insight. The world is full of hidden structures that look like air until you learn how to read them. And once you do, you can ride along the rails they make, sometimes literally, sometimes only in your understanding. Floating, not because you've escaped the rules, but because you've learned how to let the rules hold you up. Two empty plates can pull together. Seal two clean metal plates in a vacuum so good that not a single molecule remains between them. Discharge any leftover static. Make sure there's no magnet, no battery, no hidden strings, and then watch patiently as the plates drift toward each other under a force from nothing. The first time you hear this claim, it sounds like a magician's patter, but the effect is real, measured, and wonderfully teachable. Empty space can push. The explanation begins with a quiet shift in how you imagine vacuum. Instead of a dead void, modern physics treats it as a restless stage where fields never quite sleep. Even at their lowest energy, they tremble a little, producing a jittery haze of possible electromagnetic waves. Most of the time, those fluctuations are symmetric and cancel out. But when you place two conductive plates close together, you create boundaries that edit which ripples are allowed between them. Only waves that fit the gap can survive there, while outside the plates the full, unedited sea of possibilities remains. That mismatch matters because each allowed ripple carries a bit of energy and a bit of pressure. With fewer modes inside than outside, the net pressure is higher on the outer faces and lower in the gap, and the plates feel a gentle nudge together. This is the Casimir effect, proposed in the 1940s and confirmed decades later with instruments designed to be skeptical of everything but the force itself. To make the measurement honest, experimenters polish and coat the plates, remove air, stabilize temperature, and even prefer a sphere-to-plate geometry so they can avoid the nearly impossible task of keeping two large surfaces exactly parallel. A torsion pendulum or a microcantilever then registers the tiny pull as the gap is tuned through hundreds of nanometers. They must also tame imposters. Stray voltages from microscopic surface patches, residual charges, and roughness can all mimic a pull. Only when those are measured and cancelled does the true vacuum force emerge, growing dramatically as the separation shrinks. At the scale of a human hair, this force is negligible, but at the scale of microchips, it becomes a player. In micromachines with moving parts just micrometers apart, surfaces can snap together and stick under a combination of capillary forces and this vacuum pressure, an engineering problem politely named stiction. Designers learn to shape surfaces, choose materials, and set operating distances to mitigate it, and in some cases, they even explore using the effect as a non-contact latch that holds components in place without springs. The original calculation assumed perfectly conductive plates at absolute zero, but the real world is richer and that richness has been mapped. If you swap metals for dielectrics, temperature and frequency dependent, responses enter the story, captured by a more general theory developed after Casimir's first insight. And the environment can change not just the size of the force but even its sign. In a remarkable twist, experiments have shown that in the right fluid, between the right pair of materials, the net vacuum force can become repulsive. Instead of squeezing the plates together, the edited sea of fluctuations pushes them apart. Geometry, too, writes new chapters. Pattern the surfaces, and you can produce a sideways lateral version of the force that prefers one alignment over another, like a ghostly gear meshing with its partner. Make one boundary change quickly enough, and the rules take a stranger turn. If you effectively shake a mirror on timescales, comparable to the field's own rhythms, something done in practice by rapidly tuning a superconducting circuit to act like a moving wall, you can coax the vacuum's jitter into releasing real photons, a laboratory echo of the idea that boundaries sculpt the nothingness into something you can count. It's tempting to vault from all this to grand claims about cosmic energy, but good science draws a careful line. Casimir experiments measure differences in vacuum energy between configurations, not the absolute value of the vacuum's energy everywhere. They don't by themselves solve the puzzle of why the universe's expansion is so gently driven. What they do, solidly, is refute the naive idea that nothing has no consequences and offer you a lever you can actually push. There's a practical ethic hiding here. You don't need brute force to shape outcomes at small scales. You can change boundary conditions, the shapes, materials, distances, and let the background do the work. That is part of why this topic belongs in your mental toolkit alongside more familiar forces. When your phone's components shrink, when sensors get delicate, when nanostructures need to hover a precise distance above each other, the pressure of edited emptiness can no longer be ignored. And on the conceptual side, there's a more human lesson that fits the style of your day. You tend to think of influence as contact, of action as a push you can see. The Casimir effect reminds you that context can be as powerful as contact. Two plates that would otherwise be indifferent grow curious about each other when you remove distractions and define the space between them. The pull isn't a hand reaching across the gap. It's the sum of what's excluded, an architecture of missing possibilities pressing them together. The next time you hear vacuum, don't picture a sterile nothing. Picture a quiet traffic of potential that can be detoured and thinned by the constraints you choose. Set the stage and the play changes, even when the actors never touch. And when you finish this thought and look at the empty space between your fingers, resist the urge to call it useless. In a world where two empty plates can pull together, emptiness is not absence. It's a medium you can design, a background with a pulse, and a reminder that what you remove can be as decisive as what you add. Your brain predicts reality before you perceive it. Hold this thought before it slips past. The world you think you're seeing is already a corrected guess. Your brain quietly leans into the next moment, predicts what should be there, and only then compares that guess with the incoming light and sound, updating where it must and leaving the rest alone, so you feel a smooth, stable present. This isn't philosophy. It's a practical trick built into your biology to overcome delays and noise. And once you notice it, everyday experience starts to look different in the best way. Your senses are slow compared to the speed of events outside. It takes time for light to be turned into signals in the eye, for those signals to climb up the visual pathways, for the cortex to knit them into a scene. Sounds crawl a different route through the ear. Touch arrives by still another road, and the messages don't all land together. So if your brain waited passively, you'd live in a stutter. Instead, it runs a constant forecast. Higher areas send their expectations down to lower areas, like a teacher handing out answer keys before the test, and the lower areas reply only when reality disagrees. Those prediction errors dance upward and force a revision. That's why most of your cortex is not raw input wiring, but feedback highways running in both directions. And it's also why energy is used so efficiently. You spend less on confirming the obvious and more on surprising details. You can catch this in action with simple illusions and lab tricks. In the phoneme restoration effect, a cough masks part of a spoken word, and you still hear the missing sound because your brain fills the gap with what fits the sentence. In the auditory continuity illusion, a tone interrupted by noise is perceived as unbroken when the noise is the right kind, because the better guess is it continued behind the noise. In vision, the flash lag effect makes a moving object seem ahead of a flashed one, even when they were aligned, because the brain forecasts the mover's next place to keep motion looking smooth. After a rapid eye jump, a saccade, you don't notice the world smearing even though your gaze shifts 3 to 4 times a second. The system predicts the jump and momentarily dampens the blur, then stitches the before and after into a single steady scene. Even time itself gets a small adjustment. In post-diction, a later signal can alter how you remember a moment that happened just before it, not because you traveled back in time, but because the brain holds a short buffer and chooses the most coherent story once enough evidence arrives. The way a news editor waits a beat to confirm a headline. None of this makes perception fake. It makes it functional. The brain follows a simple bargain: prepare a good model, compare it to reality, and spend resources where the mismatch is large. When the model is strong, say you're reading your native language or walking your familiar route, predictions run the show and you feel fluent. When the model is weak, errors surge and you feel surprise or confusion. This same logic lets you move with grace. Before you shift your arm, a copy of the motor command, the efference copy, is sent to sensory areas to predict the touch and sight you're about to cause. That's why self-tickling falls flat, and why your voice in your own head feels more yours than a recording played back from a speaker. In hearing, your brain anticipates the beats of a rhythm and locks into them. In speech, it leans toward the syllable that makes sense in context, which is why you can follow a friend in a noisy cafe where a microphone would struggle. The evidence isn't just behavior, it's electrical. In the lab, when a series of tones repeats and then one tone deviates, your brain produces a fast mismatch signal even if you're not paying attention, a built-in alarm that the pattern your cortex assumed was wrong. When cues hint at what picture is about to appear, the very patches of visual cortex that respond to faces or places pre-activate, faint light up before light, so that when the image arrives they are already tuned. Layers in early visual areas show bursts from above before signals from the eye have finished their climb, a sign that feedback is not optional garnish, but part of the main recipe. Taken together, these pieces point to a brain that would rather be approximately right now than exactly right too late. One that earns its calm by risking small, constant bets and learning from the misses. This has practical consequences for the way you learn and the way you're fooled. If your expectations are too strong, you can hallucinate structure in noise or grab the wrong word out of a sentence. If they're too weak, you drown in raw data and feel overwhelmed. Good design, of classrooms, instruments, interfaces, meets the brain halfway by giving just enough clue to guide predictions, but not so much that error signals never rise. Good habits, curiosity, skepticism, listening, do the same for your understanding of other people, letting you hold your model lightly and update it quickly. It also reframes memory. You don't store a perfect tape. You store predictions about what matters and fill in the rest with what usually goes there, which is efficient until a detail is crucial and you realize your mind has auto-completed the story. And it gives a gentler account of disagreement. Two people with different priors will truly perceive the same messy scene differently, not because one is lying, but because each model highlights different parts of the same data. None of this excuses ignoring facts. It explains why facts alone sometimes slide off. Your model must have a place for them to land. The good news is that models can be trained. Novelty, feedback, and diverse examples teach the brain to expect a wider range of futures. So the next time reality shows a fresh face, your system will spend less time fighting and more time fitting. If you want a daily exercise, pick any episode of your routine and notice how often your mind jumps ahead. Finishing a sentence you haven't heard, reaching for a handle that isn't there, glancing left at a crosswalk before your feet arrive at the curb. Each is a small forecast that usually works and sometimes doesn't, and each miss is the brain learning where its map needs an edit. This way of seeing changes how you treat your present moment. When you feel certain too quickly, that's a strong prior talking. When a surprise annoys you, that's a healthy error signal lifting its hand. Let both do their job. You're not trying to stop predicting, you're trying to predict well. And when you close your eyes tonight, you can feel the comfort in that. Even in the dark, your mind is not empty. It is quietly proposing what the next second might bring and listening for corrections, keeping you balanced on a moving world by leaning forward just enough to make reality feel continuous, and humble enough to be corrected when the next breath arrives. Every shuffle of cards is likely unique in history. Cut a deck, riffle it, let the bridge cascade, and notice the small thrill of release, the instant those cards fall into place. You have almost certainly created a sequence no human eyes have ever seen, because the number of possible orders for 52 distinct cards is so huge that your single shuffle is like inventing a new snowflake pattern in a universe of storms and then watching it melt a moment later. Huge isn't hand-waving here, it's a cold, countable fact. The possible arrangements form a number with 68 digits, beginning with an 8 and rolling on for 67 more, and that size changes the way probability feels, turning repetition from unlikely into effectively never for any earthly schedule of play. Try a sober thought experiment. Imagine every person alive shuffling a deck once per second without sleeping, and doing this not just for a day or a lifetime, but for as long as the universe has been around. You would be left with a mountain of decks and a hum of bridges, yet you would still have sampled only a microscopic fraction of the possible orders, so small that writing it out would use more zeros than most of us are comfortable with, which is why the phrase likely unique is not marketing, but an honest summary of the odds. This scale teaches you something practical about randomness. You don't have to chase perfection to escape repetition. In a space this large, even modestly mixed shuffles will keep you from ever walking the same path twice by accident. But random isn't just big, it has texture, and the way you shuffle changes which corners of that vast space you tend to explore. The classic hand riffle, split, riffle, bridge, does a decent job, but humans are predictable. They tend to interleave near the middle, drop small clumps from the edges, and protect top and bottom cards more than they realize, which leaves gentle fingerprints like short runs or preserved neighbors. Card magicians live in those fingerprints, steering spectators toward patterns that feel scrambled, yet keep hidden structure alive for tricks. Mathematicians and card workers have studied this in detail, building models that treat a riffle as split the deck into two piles, according to a natural scatter, and let them fall together, and then asking how many such shuffles you need before the deck's order is indistinguishable from a truly random pick. The surprising answer for an ordinary deck is about 7 good riffles, fewer than folklore used to claim, and still far more than many casual games apply. On the other end of the spectrum sits a maneuver that looks professional but shuffles poorly. The perfect pharaoh, where you interleave card for card with metronomic regularity. It feels surgical, but with a fixed pattern. It cycles the deck through a small loop of orders, and even returns it to starting position after a handful of precise repeats, which is the opposite of what you want if novelty is the goal. Casinos know all this, which is why they add washing, that messy tabletop spread and smear, multiple riffles and cuts, or hand the job to machines that aim to erase human bias. They are not chasing theoretical purity so much as fairness, making every possible sequence you might reasonably encounter roughly equally likely, so no player arrives armed with hidden knowledge. This opens a second lesson. A deck of cards is a compact container for information, and shuffling is a way of writing it. Each order is like a sentence made from 52 unique symbols. The more mixed the sequence, the harder it is to compress or predict, and the more surprise it contains. That surprise is not abstract. It explains why new deals feel fresh, why games stay interesting, and why cryptographers, people who live on the boundary between randomness and structure, use shuffling machines and well-tested algorithms as metaphors for mixing data. They want the same thing you want at the table, a future that cannot be guessed from the past. Still, honesty matters. Likely unique is not guaranteed unique, and human shuffling is not perfectly unbiased. If you always riffle the same way, favor the same cuts or avoid deep interleaves, you are exploring a thin sliver of the possible deck orders, and while the chance of repeating a specific earlier sequence remains tiny, you may repeatedly visit patterns with similar features, which is why disciplined randomization, 7 mindful riffles, generous cuts, or a good shuffle machine earns its keep in tournaments and casinos. There's also a counterintuitive truth hiding in the shadow of that giant number. Because the space of possibilities is so large, your memory is irrelevant. You can't recognize a repeat even if it occurred, and you almost certainly will not notice if 2 deals share a long partial run, unless a trick or a rule calls your attention to it. The upshot is both humbling and delightful. When you shuffle, you write a once-in-history arrangement, and then erase it within minutes, letting it dissolve into the next hand. You are playing with a system where originality is the default, not the exception, and where surprise is guaranteed not by drama, but by arithmetic. That insight can change the way you teach, design, and think. If you need variety, sometimes you don't need elaborate plans. You need a mechanism that mixes well. If you need fairness, you need to know when messy enough is truly enough. If you need to detect cheating, you need to understand what real mixing looks like, so you can spot when someone is touring the same neighborhoods too often. And there is a quiet philosophical pleasure you can take from this without ever touching a deck. Your days are full of processes that sample unimaginably large spaces, language, faces in a crowd, melodies hummed on a walk, and they feel alive precisely because repetition is so rare. The card table just makes that truth visible. So the next time you square up a deck and your thumbs begin their crisp waterfall, pause for a beat and consider what you are about to do. Not just prepare a game, but draw a one-time only page from an astronomical library, a page that will flutter back into chaos as soon as you deal the first card. And yet for a few breaths it is yours alone, a small proof that in a world of patterns, genuine novelty is not precious. It's plentiful when you give chance a wide enough canvas. Light can push things. Solar sails are real. Aim a mirror at the sun and you can feel nothing on your skin. Yet the mirror feels a push, so slight you'd miss it without instruments. So steady that if you make the mirror big and light enough, it becomes an engine. And today that engine has a name and a record of flights. Solar sailing is real, and it works because light, though massless, carries momentum that can be handed off to anything that reflects it. Start with the simplest picture that doesn't lie. Sunlight at Earth's distance pours in with a constant brightness, and each photon in that stream arrives like a tiny tap. Absorb the tap, and you get a nudge. Reflect it, and you get roughly twice the nudge. The way bouncing a ball back gives your hand more kick than simply catching it. Add up those taps over a square meter, and you're in the realm of micronewtons, millions of times weaker than the shove of your fingertip. Yet physics is kind to patience. A large, shiny sail pushing on a very low-mass craft can trade force for time and win, turning a whisper into a journey. A thin, reflective sheet the size of a small apartment, weighing a few kilograms, can generate accelerations of fractions of a millimeter per second squared. That sounds like nothing until you let it run for days and weeks, letting the velocity build without burning a drop of fuel. The art then becomes 2 things at once. How to build a sail that is both large and feather-light, and how to steer a force that always points away from the sun into the path you actually want. On the first count, engineers turn to films only microns thick, aluminize plastics like Mylar, Kapton, and newer space-rated polymers, and support them with booms that are themselves rolled tapes or composite spars designed to spring outward on command. Wrinkles, tears, and thermal expansion are not annoyances but central problems because a crease can twist the thrust, and a hot-cold cycle can slacken the sheet until it flutters. On the second count, steering borrows a page from ocean sailing. You tack on light. Tilting the sail changes the thrust vector. In clever geometry, diagonal veins at the corners, shifting the center of pressure relative to the center of mass, lets you crank the orbit's size up or down, or change the plane you ride in by using sunlight the way a sailor uses wind relative to a keel. Get closer to the sun and the pressure strengthens. Back away and it weakens with distance. So one powerful strategy is the sun diver maneuver. Fall inward to a close approach where radiation pressure is fierce. Rotate the sail to catch the maximum push and turn that burst into a climb toward a far objective. None of this is only on paper. In 2010, a space agency flew a sail named after a Greek messenger god and proved the concept in deep space, steering with trapped light and cameras that watched tiny liquid crystals flip black to clear as part of a clever attitude system. Less than a decade later, a crowd-funded mission unfurled a sail about the size of a boxing ring in Earth orbit and showed not just that sunlight could keep it aloft, but that daily, disciplined adjustments to the sail angle could raise and lower parts of the orbit as planned. A quiet, public demonstration that momentum from photons can be harnessed with off-the-shelf ingenuity. Both flights taught hard lessons. Deployment is everything, shiny isn't enough, and area-to-mass ratio is your fuel tank. The promise grows when you realize that continuous, gentle thrust does things chemical rockets can't. Rockets are sprinters. They fire. They kick you onto a new path. They fall silent. A sail is a marathoner. It changes your path slowly but always, and that means missions that require long, patient reshaping of orbits, hovering out of a planet's orbital plane to watch pole caps, holding a position off the Sun-Earth line to stare into the polar aurora, spiraling outward to the asteroid belt without refueling, become practical for small budgets. A sail can loiter near the line between Sun and Earth to monitor solar storms earlier, or hang above Earth's poles in a way that would be brutally expensive with fuel. For exploration further out, sails can escort small probes to multiple targets, nudging their orbits into encounters one by one. And because the engine is sunlight itself, the only propellant you carry is structure. There's nothing to run out. Push the idea harder and it enters science fiction's front yard with science's paperwork in hand. Drive the sail, not just with the sun, but with a directed laser from Earth or the moon. And the pressure rises by orders of magnitude. That's the sketch behind proposals to fling gram-scale probes to nearby stars within a human lifetime of acceleration and cruise, which compresses the material challenges into a different shape. Super reflective, thermally robust sails the size of umbrellas, exquisite beam pointing, and gossamer electronics that can ride the shock of a staggeringly bright push. Even if that interstellar dream takes time, nearer-term laser boosts could help sails climb out of Earth orbit faster or break incoming craft without tanks of propellant, by aiming power where and when it's needed. Honest enthusiasm requires acknowledging the edges. Sails don't work well in deep shade or far from the sun without enormous area. They are sensitive to dust, charging, and micrometeoroids. They test the patience of operators because the feedback loop is slow, and they benefit from navigation support that can measure tiny accelerations and adjust the attitude accordingly. Materials age, coatings darken, booms can warp. The very reflective films that make the engine work also make thermal control tricky as the craft passes from full sunlight to eclipse. But each of those edges is an engineering frontier rather than a showstopper, and with every demonstration, the community learns where to sand and where to reinforce. There's also a quiet cultural lesson tucked inside the physics. For a century, we've told space stories in the language of explosive fuel and short bursts of glory. Sails rewrite that story in the language of patience, surface area, and alignment. They reward designs that are wide rather than heavy, controls that are rhythmic rather than impulsive, goals that accept weeks of steady work over minutes of brute force. If you're a builder or a student, this can reshape your instincts. Sometimes you don't need more power, you need more surface and a better angle. Sometimes the environment provides the energy if you design to catch it. And if you're simply a curious mind watching from Earth, there's a deeper way to hold the idea. Light is not just what lets you see, It is a breath that can move things very softly, very surely, across millions of kilometers. A constant river you can step into with a mirror spread thin as a dragonfly's wing. Think of a sail opening like a silver flower in the black garden of orbit, feeling for pressure in a place with no air, and then, almost imperceptibly at first, beginning to drift in a direction chosen not by fire, but by the angle of a sheet to a star. That's the kind of propulsion that teaches more than mechanics. It teaches a posture. Catch what's already there, hold it well, and let persistence do what force cannot. When you close your eyes tonight, picture a square of light held taut, turning its face to a sun it will never touch. And remember that motion can come not only from pushes you feel, but from patience you cultivate, out there and, if you choose, in the quieter engineering of your own plans. Bananas are slightly radioactive. Hold a Geiger counter near a banana and you'll hear shy ticks in the speaker. Soft, patient reminders that natural doesn't mean radiation-free, and that the world you live in hums with tiny decays so ordinary you've grown up inside them without noticing. The surprise is not that a banana is radioactive, but that you are too, and that this shared glow is both measurable and harmless at the levels we're talking about. The reason is mostly potassium. Your nerves, muscles, and heartbeat rely on potassium ions to fire and reset. Bananas are famous for carrying plenty of it, and a tiny fraction of all potassium on Earth is a long-lived isotope called potassium-40 that happens to be unstable. Each second, a few of those atoms in the fruit, and in your own cells, quietly transform, tossing out a small burst of energy as a beta particle and sometimes a gamma ray. If you want an honest sense of scale, think of activity as simple counting. A becquerel is 1 decay per second. A typical banana's potassium produces on the order of a dozen or so decays each second. Your body, because it holds far more potassium than a banana, and also carries a smidge of carbon-14 from the air and plants you've eaten, glows at something like several thousand decays per second, every second, for your whole life. That sounds like a lot until you remember how unbelievably small an atom is, and how perfectly adapted biology is to such a background. Compared to the radiation you get from the ground beneath you, from granite and brick, from radon in basements, from cosmic rays at cruise altitude, and from medical imaging when you need it. The contribution from a banana, or from your body's potassium, is a rounding error. People sometimes translate all of this into an everyday unit called the banana equivalent dose. Eat 1 banana, get roughly 1/10 of a microsievert, the kind of dose you'd also get by living for a few hours at sea level, or by sleeping next to another human for a night. Because yes, other people are slightly radioactive too, but there's a deeper truth that the catchy unit can hide. Your body keeps potassium concentration within tight limits. If you eat an extra banana today, your kidneys will quietly remove the surplus tomorrow. That means your long-term internal radioactivity from potassium hardly budges. You're swapping in new potassium atoms for old, not stacking risk like coins. This is why physicists use the banana as a teaching story rather than a warning label. It helps you feel the scale of things. If a banana is about 1/10 of a microsievert, a dental X-ray is in the tens of microsieverts. A transcontinental flight is a few hundred, and a chest CT scan is in the thousands. Everyday background adds up to a couple of thousand per year, depending on where you live. The banana's tick, by comparison, is a whisper. That whisper is useful in the lab. Teachers demo radioactivity with potassium-rich salt substitutes because they set off counters gently and safely. Customs officers sometimes see radiation monitors blip from shipments of bananas or cat litter and log it as norm, naturally occurring radioactive material. Even Brazil nuts, which draw up tiny amounts of radium from deep soil through their giant taproots, can register higher than a banana. Not because anyone laced them with danger, but because some plants are better at concentrating trace elements than others. Knowing this doesn't trivialize radiation. It gives you the vocabulary to judge it. The word itself carries a lot of fear, and not without reason. High doses delivered quickly are dangerous, and some isotopes that lodge in bones or thyroid tissue require special care. But the physics that scares us in headlines is the same physics that keeps your heart beating and your neurons spiking. The trick is to separate dose from drama. Dose is how much energy per kilogram your tissues actually absorb, adjusted for the biological impact of the type of radiation. A banana is not a uranium fuel pellet, and your body's potassium is not fallout. Its decays are sparse, spread out, and woven into metabolism that evolution has always known. If you want to see this with your own eyes, run a simple experiment the next time you visit a science museum. Compare the counter's clicks near a banana, near a granite countertop, near a bag of fertilizer, and near the open air. You'll learn in minutes what takes years to feel instinctively. That background radiation varies by location and material, that it is everywhere, and that context matters. Step away from gadgets, and the story gets even more interesting. Potassium-40 has a half-life of over 1 billion years, which means half of a given batch takes that long to decay. It is a relic of stellar alchemy, part of the natural mix forged before the Earth formed. Carbon-14 is made high in the atmosphere when cosmic rays strike nitrogen. Plants breathe it in as part of carbon dioxide. Animals eat the plants, and so it becomes a clock that ticks inside wood, bone, and you. Archaeologists date ancient fires and burials by measuring how much of that ticking remains. Doctors use carefully chosen isotopes to track blood flow and metabolism. Smoke detectors once relied on a speck of americium to ionize air and sense a change. Industry inspects welds and cargo with sources calibrated to give a clear picture at a safe distance. In other words, the phenomenon you're meeting through a banana also powers tools that save lives and read history. There's a quiet psychological lesson in all this. Once you hear radioactive, it's easy to picture glowing green goo and villains in hazmat suits. The banana softens that reflex. It teaches you to ask how much and what kind before you decide what to feel. It nudges you toward proportionality, the same habit that makes you a better thinker in other domains. Judge by scale, by mechanism, by evidence, not by label alone. And it invites a kinder understanding of your own body. You are not a fragile ghost in a hostile bath. You are a living system in balance with a planet that has always had a background glow. Your cells repair damage every day. Your DNA has proofreading and patching crews. Your physiology treats potassium like a precious instrument to be tuned, not a threat to be purged. If there's one practical takeaway to carry into your kitchen, it's this. Food choices are about nutrition, not radiation. Bananas are good because of fiber and vitamins, and that steady potassium your heart likes, not because they scare a Geiger counter, and eating them will not make you more radioactive in any meaningful way. If you want to play with the idea, think of your life as a low, steady song. Granite hums in one key, air travel adds a harmony, medical scans add a bright bar when they're necessary, and inside it all, you and your bananas contribute a faint, ancient note that has been playing since long before humans walked the earth. Knowing that doesn't make danger trivial. It makes your understanding precise. It lets you close the fruit bowl with a small smile and a better question the next time a headline shouts the word radiation. What's the dose? What's the source? And how does it compare to the quiet music you already live in? Sonic black holes, horizons you can build in a lab. Imagine building a horizon on a tabletop. No stars collapsing, no impossible gravity, just a quiet stream of matter or light arranged so that ripples on it can move one way but never the other. And when you lean in close, you realize you're looking at the lab-made cousin of a black hole. A sonic horizon that traps sound the way an event horizon traps light. The recipe is surprisingly clear once you switch from objects to signals. In a fluid, a ripple can only swim as fast as the speed of sound in that fluid. If you drive the fluid itself faster than that speed, any ripple trying to fight upstream is carried back downstream no matter how hard it tries. And the boundary where the flow first outruns sound becomes an acoustic point of no return. Physicists sometimes nickname these setups dumb holes, not as an insult, but because sound inside cannot speak to the outside world. You can build the effect in several media. Push water over a carefully shaped obstacle so the surface flow becomes supercritical and blocks upstream waves. Send an intense optical pulse through a fiber to create a moving change in refractive index that acts like a horizon for other weaker light. Or most delicately, sculpt a Bose-Einstein condensate of ultra-cold atoms so part of it flows supersonically past a narrow throat while the rest remains subsonic, creating a sharp line where phonons, the tiny quanta of sound, cross from free to trapped. The goal is not to fake gravity, but to mimic the rules that matter near a horizon. In all these cases, the equations for how little excitations propagate can be rewritten to look like the equations for fields living in curved spacetime, with the flow playing the role of geometry. That similarity opens a door to one of the most haunting predictions of black hole physics: Hawking radiation. The idea that horizons are not perfectly black but glow faintly because quantum fluctuations near the boundary can create paired disturbances, with one partner escaping and the other falling in. In a lab, you're not looking for infrared light from a billion solar mass monster. You're listening for matched phonons at a temperature set by how sharply the flow changes at the horizon and by the medium's own microphysics. Researchers learn to map correlations in the noise, to look for the telltale handshake between quanta on opposite sides of the boundary, and to show that the escaping and trapped partners share an entangled life that gives the glow its thermal character. The best demonstrations so far have come from condensates chilled to nanokelvin temperatures, where background chatter is quiet enough that the horizon's whisper can be picked out. By creating a steady supersonic region and recording the tiny density ripples, teams have reported thermal spectra with the right shape and, more impressively, mutual correlations between inside and outside that match what the Hawking story expects. When two horizons are formed close together, an outer black hole entrance and an inner white hole exit, the cavity between them can even act as a black hole laser, bouncing phonons back and forth and amplifying them until the signal rises above the murmur. A vivid reminder that horizons are about kinematics, the rules of motion, not mystique. Water channel experiments have shown their own versions of horizon behavior, including mode conversion, where a wave approaching the blocking current morphs into a different kind of wave that can escape. A classical shadow of the quantum process, optical analogues have turned moving refractive steps into blockers that shift and scatter light in characteristic ways. Honesty matters here. A sonic black hole is not a gravitational one. There is no singularity inside, no crushing tides, no warping of time. And because real materials have dispersion, the analogy bends at very high frequencies. That means the lab will never prove Hawking's cosmic calculation in a literal sense. What it can do is test whether the radiation's key features survive when you change the microscopic details, whether horizons generically stimulate paired quanta with a thermal fingerprint, whether the temperature is governed by the gradient at the horizon, whether entanglement straddles the boundary as predicted. The evidence so far is encouraging and not without debate, which is exactly what you want from a young field. Independent groups probing different media, cross-checking methods, arguing over backgrounds and statistics, and learning how to build cleaner horizons with cleaner readouts. For you, the non-specialist, there are 3 durable takeaways that make this more than a party trick. First, black hole behavior is about signals and speed limits. Wherever a flow outruns the waves that carry information, you can draw a horizon. Whether that flow is water, sound, light, or something more exotic that reframes the cosmic idea in a language you can prototype. Second, quantum field theory near horizons is not a purely astronomical story. It is a laboratory one, with knobs you can turn and diagnostics you can refine, which means ideas about particles emerging from the vacuum in curved space-time can be confronted with data rather than left as distant speculation. Third, horizons can be engineered into devices, not tomorrow's engine, but tools that control waves without touching them. Filters, one-way channels, amplifiers that harvest black hole lacing, all by shaping the background so that what you want cannot propagate backward. If you want the gentler lesson that threads through these facts, it is this. Some of the grandest words in physics are really statements about context. When you see a tabletop hole holding sound captive, you realize that nothing escapes is not a spell. It's a consequence of what can move where, and of how a boundary edits the space of possibilities. You begin to ask sharper questions everywhere. What are the signals here? What are their speed limits? And can I change the background so the limits do the work for me? Then the lab horizon stops being an imitation and becomes a teacher. It tells you that the universe's strangest edges can sometimes be brought close and made audible, that careful design can turn absence into function, and that the line between deep theory and practical craft is thinner than you think. And when you let the image fade, the quiet channel, the flowing atoms, the flicker of light trapped against a moving mirror, you can carry a fresh kind of awe into the night. Somewhere, real black holes are whispering particles from their rims into space. Here, with cold hands and clear eyes, you learned how to make a horizon sing back. The moon is drifting away, days are getting longer. Listen for a slow, planetary metronome you've never noticed. Each night the moon tugs the oceans into bulges. Earth's spin drags those bulges slightly ahead, and that tiny misalignment lets the water pull. back on the moon like a rope being yanked from the side, stealing, a whisper of Earth's spin and paying it, forward to the moon's orbit, so our days grow longer by fractions of a heartbeat, while the moon drifts away by a few centimeters each year. A trade quietly audited by lasers and fossils alike, and so steady that it has been sculpting the calendar for hundreds of millions of years. The mechanism is simple once you picture it. Because Earth rotates faster than the moon circles, the tidal bulge is carried a bit in front of the moon's position. Friction with the seafloor and coastlines keeps the bulge from freely sloshing, so it tugs on the moon forward along its path, giving the moon extra orbital energy and nudging it to a slightly larger orbit. And at the same time, the reaction torque slows Earth's spin by a hair. This exchange is not guesswork. Retroreflectors left on the lunar surface by astronauts and robotic landers let observatories ping laser pulses off the moon and time their return to fractions of a billionth of a second. A tape measure so clean it shows the moon's mean recession at a few centimeters per year, about the rate your fingernails grow. On the home side, the slowing of Earth's rotation shows up in places you wouldn't expect. Sediments laid down in tidal flats preserve fine, rhythmic layers that repeat with the tides, the month, and the year, and some ancient stacks reveal that a year once contained roughly 400 day-night cycles. Coral and mollusk fossils record daily growth rings grouped into monthly and yearly bands, and counts from the Devonian period point to days around 21 to 22 hours long. The match between modern laser ranging and deep-time geology isn't just poetic, it's a cross-check. The present rate of lunar recession is influenced by today's ocean shapes and depths, which set how efficiently tides dissipate energy, while the long average across many continental configurations still lands on the same story. Give away spin, gain orbit, stretch the day. That efficiency, by the way, is a live variable. When continents crowd together, or ocean basins are at resonance with the tides, the global braking grows stronger, and when the world's geography is friendlier to quiet seas, it weakens, which means the day doesn't lengthen at a perfectly constant rate through history. Even now, short-term wiggles ride on the long trend. Wind patterns can trade angular momentum with the solid Earth. Ice and groundwater shift mass toward or away from the equator. Great earthquakes subtly redistribute mass, all tiny effects that can speed or slow the planet by milliseconds. But the tide-driven drift keeps pushing the clock one way over centuries. You feel the bookkeeping in a modern, practical way whenever timekeepers adjust civil time to track the sky. Atomic clocks tick with exquisite steadiness, while the spin of Earth, nudged by tides and weather, meanders, and occasionally the world agrees to slip a single second into our official time so that noon stays close to when the sun is high. The moon itself is already tidally locked, its face turned to us by the same torque that is slowing Earth, so we always see nearly the same lunar Maria and highlands. Our planet is headed, in principle, toward a far future where one Earth rotation would equal one lunar month, and both bodies would stare at each other. But that equilibrium sits tens of billions of years away, long beyond the sun's comfortable phase, and the sun's own tides and future evolution will rewrite the endgame first. What makes all this worth learning isn't just the novelty that days are getting longer. It's the way multiple lines of evidence nest together. Lasers timing distance to the moon to the millimeter, tide gauges and satellite altimetry tracking how oceans slosh, growth bands in ancient shells counting dawns we will never see, clay rhythmites tallying cycles of tide and season, and centuries of eclipse records in old calendars and chronicles that, when compared to modern calculations, reveal slight drifts in Earth's spin. The picture is also rich with useful consequences. Tidal friction is a hidden heat source. On Earth, it dissipates energy roughly comparable to the output of a few large power stations spread across the globe, and on other worlds, it can dominate geology altogether. Jupiter's pull needs Io until it erupts, and a similar rhythm keeps the hidden seas of Europa and Enceladus liquid. For us, the lesson is gentler and closer to home. The length of your day is not a fixed gift, but an emergent property of a moving, flexing planet entwined with its companion. Calendars work because we agree on them, not because the heavens are static. And the moon you watch from a balcony tonight is not exactly where it was for your great-grandparents. Nor will it be where it is now for your great-grandchildren. If you want a feel for the numbers without any symbols, try this mental calibration. At today's pace, it takes on the order of a human lifetime for the day to lengthen by just a couple of milliseconds. But stack enough lifetimes, and it adds up. Go back to when ancient reefs were alive, and a schoolchild would have counted many more sunrises between birthdays. And there's an attitude in this that's worth keeping. Big changes can be made of tiny, faithful steps. The moon doesn't yank itself outward. It rides a constant whisper of torque. Earth doesn't slam to a slower spin. It yields by hairs. In that slow patience, oceans learn the shape of the coasts. The coasts learn the patience of stone and time. The human time we schedule and celebrate quietly adjusts to a rhythm that began with the first tides. Close your eyes and you can almost feel it. A planet breathing through its seas, a satellite receding with courtly grace. And your day, this very day, a hair longer than yesterday's, long enough to hold one more small thought about how motion, friction, and gravity collaborate to write the hours we live in. Rainbows are full circles you rarely see. Stand on a hillside after a storm, and you'll swear the sky has painted a giant arch just for you. But the quiet truth is stranger and more beautiful. A rainbow is a full circle centered on the point exactly opposite the sun from your eyes, and you almost never see the lower half only because the ground gets in the way. Lift yourself high enough, on a mountain ridge, a skyscraper, or in an airplane with rain or mist below, and the circle appears whole. A glowing wheel of color wrapped around your own moving shadow. The geometry is relentless and personal. Sunlight enters countless raindrops, bends as it slows in water, fans into colors because each hue is nudged by a slightly different amount, reflects once off the back of the drop's inner surface, and then bends again on the way out. Among all the rays that do this, the brightest ones leave the drop clustered near a particular angle from the incoming sunlight, roughly the width of an outstretched hand held at arm's length. And because every drop that sits on that cone sends light to your eye at that same angle, you trace a perfect circle when you turn your head. Red on the outside where the angle is a touch wider, violet inside where it is a touch tighter. That's why a rainbow feels like it follows you. The center of the circle is the antisolar point, a spot in the sky opposite the sun drawn through your head, and nobody standing next to you sees exactly the same bow because their center is shifted through theirs. Once you notice this, puzzles untangle. A rainbow looks tallest near sunrise and sunset because the sun is low, so the circle's center is just beneath the horizon, and more of the ring rises into view. At noon, the center sinks far below the ground, burying most of the circle and making sky bows rare. The distance to a rainbow isn't fixed either. It's not a colored wall out there in space, but a direction. Fresh drops closer or farther along the cone will do. So as you walk or drive, the location travels with you, and any thought of arriving at the end is like trying to reach a reflection. The double rainbow, when it shows, adds a second lesson in the same language. Some rays reflect twice inside the drop before emerging. That extra turn flips the color order and sends the second bow a little looser and fainter above the first, with a darker mid-band in between, Alexander's dark band, carved by the fact that rays between those two favored angles are kicked away from your line of sight. Look closer on exceptionally fine days, and you may catch supernumerary fringes, pale, pastel bands snuggled just inside the main bow, born not from ray geometry, but from light's wave nature. Neighboring paths through a droplet interfere and add or cancel in a gentle ripple of brightness that small, uniform drops can make visible. Shift media and the family grows. Tiny fog droplets smear colors into a wide, ghostly fog bow, nearly white because the drops are too small to separate the hues cleanly. Moonbows, lit by bright moonlight, are rare and faint enough to need long exposure eyes, but they are the same circle written softly in silver. Around an airplane's shadow, where the cloud is made of tiny droplets, you may see a compact halo called a glory, a different interference trick that rings your own silhouette like a target. Separate cousin phenomena, halos formed in ice crystal clouds, make rings and arcs around the sun or moon at different angles and with different rules, a reminder that the sky's geometry set by crystal shape is as decisive as the raindrop's curve. If you want the most practical way to catch the full circle, remember 3 conditions. The sun must be behind you and not too high. You must be elevated with raindrops or spray below your eye line. And the air between you and those drops should be clear. Waterfall overlooks, and stadium mist can be perfect. And the spray from a garden hose in late afternoon light can teach the same lesson in miniature, letting you walk the glowing ring across your lawn. A polarizing filter adds another piece of the puzzle by turning the sky around the bow darker or brighter as you twist it. Rainbow light is strongly polarized because of how it leaves the droplet. So a simple pair of sunglasses can make colors pop or fade and prove that the glow carries an orderly electric field direction, not just a hue. Honest details keep the story grounded. Falling raindrops are not teardrops. They are squashed spheres, slightly flattened at the bottom, and that subtle shape, along with ripples on their surface and differences in size from place to place, softens and broadens the colors. Large, smooth drops make a vivid, narrow band, while clouds of small drops wash the spectrum into a gentler smear. Because the cone's angle is fixed by water's optical properties rather than distance, a rainbow can lie just beyond your windshield or beyond a field. It depends only on where the droplets that satisfy the angle happen to be. So police photos, truck spray, and fountain plumes sometimes hide miniature bows you can predict once you know what to look for. Turn your back to the sun, check the angle off the opposite point, and move until the mist sits at the right place on the cone. There's even a weather hint hidden in your view. If you face a morning rainbow, the rain is likely moving away. If you face one in the late afternoon, the rain may be coming or lingering. And when you hear legendary talk of a third or fourth rainbow, know that they exist, but play hard to see. The next two arcs, produced by 3 and 4 internal reflections, sit on the sun's side of the sky and drown in glare unless conditions are exceptionally gentle and your patience is long. The deeper lesson tucked in all this color is not just that rainbows are circles. It's that the circle is a map drawn by your position and the physics of light. And once you carry that map, you can make the world cooperate. Climb above the spray, move until the mist is under your anti-solar point, and the wheel appears. Tilt a lens and the colors intensify. Narrow your eyes and you will spy faint extra bands you once thought impossible. Then the folklore that says you can never reach the bow finds a kinder correction. You can reach it any time because it was never out there in the first place. It was always a conversation between sunlight, raindrops, and the place you stand. Hold that the next time the air clears and the ground steams under a parting cloud. Somewhere in the glowing miles behind you is the sun. Somewhere in front is a shell of wet air, and between them is your viewpoint tying the geometry together. If you change your height, the shell you can see changes. If you fly, the circle closes. If you turn, the map rotates around your own shadow. In the soft knowledge that follows, the rainbow stops being a rare gift and becomes a repeatable instrument, a proof that patterns appear not only because nature is generous, but because you learn where to look, and that what you call wonder is often the feeling of a rule clicking into place. An invisible circle suddenly made visible by rain, sun, and you. You faintly glow in the dark. Switch off the lights, let the room settle, and imagine a camera so patient it can sit with you for an hour without blinking. If it were sensitive enough, it would see a ghostly film over your skin, a faint, flickering haze that flows with your breath and pulses with your day, because living chemistry gives off a trickle of visible photons, and you, right now, are quietly glowing. This isn't the showy blue of deep-sea creatures, or the neon of a jellyfish, and it isn't the warm infrared heat that night vision goggles love. It's ultra-weak visible light born from ordinary metabolism, so dim your eyes will never catch it unaided, yet so reliable that researchers can photograph it with cooled detectors in pitch-black rooms. The origin sits in the engine room of your cells. When oxygen helps you harvest energy from food, side reactions make short-lived excited molecules, singlet oxygen here, a jittery carbonyl there, and when those excitations relax, they release tiny packets of light. Lipids in cell membranes can peroxidize and toss off a photon during repair. Flavins and other helpers in the respiratory chain can fall from an excited state and glow for a heartbeat of a heartbeat. Immune cells in a burst of activity leak more of these flashes as they produce reactive oxygen to fight invaders. Each event is unimaginably small, but you carry trillions of cells, and the sun becomes a measurable drizzle. Depending on the spot and the moment, the skin may emit tens to a few hundred photons per square centimeter each second, with a color tilt often strongest in yellow-red wavelengths. That is still far below what a dark-adapted human eye can see, which is why experiments happen inside light-tight boxes with black walls. The detectors chilled until their own electronic noise grows quiet, and the subject sitting still while the camera integrates for long minutes. When researchers do this carefully, patterns emerge. The face and hands often shimmer more than the torso, because of higher metabolic turnover and thinner tissue. The emission rises through the day and dips at night, tracking circadian rhythms that also steer hormones and body temperature. Stress, vigorous exercise, or local inflammation can nudge the glow upward, while antioxidants can damp some pathways, all consistent with the idea that this light is a side channel of oxidative chemistry rather than a separate lamp switched on by design. What you see in those images is not an aura, it's physiology, a non-invasive map of how busy certain reactions are and how well your cellular cleanup crews are keeping up. The same principle shows up far beyond human skin. Leaves shine with ultra-weak light that ebbs and flows as photosynthesis hiccups and recovers. Seeds and sprouts briefly brighten during germination. Fruits and fish glow weakly as they age. So food scientists sometimes use this trickle as a freshness indicator. In labs, immune cells emit more during a respiratory burst. And tumor lines can differ from healthy lines in their photon signatures, hinting at diagnostic use if we learn to standardize the conditions and interpret the spectra with care. There's even a sister phenomenon called delayed luminescence. After you briefly light a sample with gentle illumination, it can afterglow for seconds to minutes as excited states unwind, which gives another window into the architecture and stress of tissues. Against this practical clarity stands a swirl of overreach you should learn to sidestep. You can find grand claims that bodies converse with light, that the brain signals in photons like a hidden fiber optic network, or that a healer's hands can dial the glow at will. So far, the evidence says otherwise. Yes, neurons and other cells can produce and scatter a few visible photons, and proteins in the eye or brain can, in principle, interact with light. But the numbers are brutal. Photons scatter, tissues absorb, and the rates measured are too low and too noisy to act as robust long-distance couriers inside a head that already talks in ions and electrical pulses engineered by evolution to be fast and precise. That doesn't make the glow trivial. It makes it honest. Think of it as a lucky byproduct, a free diagnostic that biology offers if you know how to listen. Listening takes craft. A camera must be calibrated with a known light source. The room's air must be clean and still. The lens and window glass must be chosen so they don't fluoresce under stray wavelengths. Skin must be washed gently to remove lotions that can fluoresce or absorb in confusing ways. The analysis must account for the detector's own dark counts and for the background light that even a closed room breathes. When those details are respected, the images become coherent. You can see the slow fade after a patch of skin is exposed to light. You can see the rise after a cold press or a mild stressor. You can see hotspots that match blood flow and metabolic maps. If you care about the numbers, sit with an intuition instead of a formula. A whole human might emit on the order of a few 100,000 to a few million visible photons each second. So little that, spread over your surface, it would take many seconds for even the best dark-adapted eye to collect the bare minimum to notice a flash. And yet for a machine that never blinks, those seconds add up to a readable story. This story isn't meant to make you anxious about oxidative stress under every lamp. It is meant to give you a calmer literacy. Sunburned skin will glow more until it heals. Not as a judgment, but as a tally of chemistry. A hard workout may leave your muscles brighter in the minutes after, a signature of effort and repair. Aging skin may shift its spectrum and yield, and so may a bruise as it resolves. In medicine, the hope is to use these shifts to flag problems early, or to monitor treatments without needles or dye. In ecology, the hope is to watch plants respond to drought and disease without cutting leaves. You can even bring the lesson home at a gentler scale. Know that cheap biophoton cameras sold online mostly chase noise, and that the real instruments look more like astrophotography rigs aimed at your skin than like phone filters. Know that if you shine bright light on yourself and then photograph the afterglow, you're reading delayed luminescence, not your baseline. Know that the like-for-like comparisons, same person, same conditions, repeated over time, are what carry meaning. There is a softer reflection tucked in all this measurement. We are used to thinking that important signals are loud. The thump of a heart, the spike on a monitor, the hot red of a scan. But here the signal that reveals how you burn and mend is almost silence. You live surrounded by light you do not see, carrying a candle you do not feel, and that candle brightens and dims with your days. If you let that image in, it subtly rearranges the way you hold your own body. Not as a black box, but as a lantern whose glass is thick and whose flame is careful. a lantern that has always been lit, even in rest. Tonight, when the room is dark and you're settling towards sleep, you can borrow the patience of those cameras and imagine the field of soft sparks that your chemistry would show. Tiny notes of repair, whispers of effort, a slow tide that rises with the afternoon and falls with the night. And you can take comfort in the ordinariness of that glow. Not mystical, not marketable, but real, measurable, and quietly beautiful evidence that life, even at its gentlest, leaves a trace of light. Information has weight. Erasing bits releases heat. Open a text file and press delete, and it feels like nothing happens except a blink on a screen. Yet in that ordinary keystroke, the world makes a quiet trade. Some information is rubbed out, and a pinprick of heat must appear somewhere, because forgetting is a physical act with a minimum price that nature refuses to waive. This is the content of Landauer's principle, a simple but stubborn rule that says whenever you compress many possible states into one, whenever you reset a memory cell to 0, no matter what it was before, you must dump a tiny, specific amount of energy as heat into the surroundings. And in that sense, information has weight. Not a weight you can feel in your hands, but an energy cost that, through the famous link between energy and mass, even corresponds to an unimaginably small mass. To feel what this means without equations, think of a single memory bit as a coin hidden under one of 2 cups on a table. Reading the bit is like lifting a cup and seeing where the coin is. That can be done gently. But erasing the bit is different, because you insist that after you're done, the coin must be under the left cup regardless of where it started. That insistence squeezes away possibilities and the entropy that went with them. And the second law of thermodynamics quietly leans over your shoulder and presents the bill to pay for the lost possibilities. You must warm the environment by at least a few times 10 to the minus 21 joules per bit at room temperature. That number is so small it's hard to respect. Erase all the bits on a 1 terabyte drive and the absolute minimum heat you owe the universe is only on the order of tens of nanojoules, less than the energy in a single step of an ant. Yet the key isn't size, it's principle. No amount of clever engineering gets that number down to 0, as long as the operation is logically irreversible. Real devices are nowhere near this limit. Your laptop's processor wastes millions to billions of times more energy per logical operation than the minimum, because they must switch quickly, overcome noise, and deal with resistance, stray capacitance and leakage. But the flaw matters. It tells you there is a fundamental reason computers heat up when they work, and an ultimate incentive to redesign how we compute if we ever hope to keep shrinking and speeding without cooking our chips. You can watch the principle come alive in experiments that are small and careful enough to hear physics whisper. In one landmark study, researchers trapped a tiny bead in a liquid using a laser tweezer that created a double-well energy landscape, like 2 dimples in a slope, and used feedback to push the bead reliably into a chosen dimple, an analog of forcing a bit into 0. By measuring the minuscule jostling of the bead and the work done by the control system, they saw exactly the expected heat appear in the surrounding fluid. Right on cue with the theoretical lower bound. Similar ideas have been demonstrated with single electron devices and quantum dots. The lesson is not just that heat shows up, it's that it shows up precisely when you discard information. That is why a famous thought experiment about a mischievous demon that sorts fast and slow gas molecules, seemingly extracting free work from randomness, is resolved not by forbidding observation, but by charging the demon for erasing its notebook. To run a full cycle and be ready for the next trick, the demon must reset its memory, and the heat bill paid at that moment saves the second law. This separation between reading and forgetting hints at a way out. If you avoid erasing information, if you make your computations logically reversible so that every output implies a unique input, nature does not force you to pay that minimum heat cost simply for moving symbols around. Any energy you dissipate then comes from imperfections and speed, not from logic itself. In the 1970s, theorists showed how to build such reversible circuits in principle, and modern research keeps chasing practical schemes. Adiabatic logic, superconducting loops, nanomechanical gates that trade speed for gentleness. None of these are ready to replace your phone's processor, and real systems always leak and jitter, but the direction is clear. The closer our machines come to that reversible ideal, the closer we can push toward the thermal floor, and the more work we can squeeze out per joule. The phrase, information has weight, can mislead if you picture a hard drive getting literally heavier when you save a photo. The honest version is subtler. Storing a bit doesn't require a fixed energy, but erasing a bit does. There is a minimum. Heat you must exile when you insist on ignorance. So if you treated that heat as energy and converted it into an equivalent mass using the famous relation between energy and mass, you could say that the cost of erasing has an associated mass so tiny it makes a dust mote look like a planet. Still, the metaphor is useful because it forces you to place information back into the physical world where it belongs. Bits are not ethereal. They live in voltages, charges, magnetized domains, mechanical positions, photon phases. They must be created, maintained against noise, and, this is the crucial point, sometimes destroyed to make room for the next calculation or to synchronize a device before a new task. That destruction is where the heat lives. You can track the consequences right up to present engineering. Why are data centers hungry for power and cooling? Because they not only move bits, they constantly reset, compress, sort, and overwrite them. Why are ultra-low power sensors designed to sleep, wake briefly, avoid unnecessary writes, and batch operations? Because every avoidable erasure saves energy twice. Once at the logic level, once at the system level, where less heat means less work for cooling. Why does error correction, vital for reliability, raise energy costs? Because to check and fix data, you inevitably create and then erase scratch space, pushing against the same flaw. And if you look further ahead, toward exotic ideas like in-memory computing, neuromorphic chips, or even biological processors, you find the same moral. Architectures that minimize needless forgetting are more likely to thrive in a world where energy budgets are tight. For you, as a thinker, there's a softer payoff. The next time a file vanishes with a keystroke, you can hold two truths at once. At human scale, you lost a line of symbols. At physical scale, the machine performed a small act of housekeeping that could not be perfectly free. A tiny warming that paid for making many possibilities into one. And that can change how you design your own systems of thought and work. Do you erase prematurely, throwing away context you'll have to recreate at cost? Or do you keep computations reversible for longer, preserving paths so you can backtrack without paying twice? Even outside technology, the metaphor encourages thrift. Be careful what you discard if you might need it. And when you must erase, understand that you're buying simplicity with energy. Tonight, when the hum of your devices fades and you set a window to clear cache, remember what that click really means. A small, necessary release into the room, paid to keep the future orderly. A whispered admission that even ideas have to live on matter, and that tidiness, in physics as in life, comes with a bill you settle in heat. Most of your mass is gluon energy, not particles. Pick up a book, feel its weight in your hand, and know this. Most of what you're lifting isn't stuff in the everyday sense. It's energy, knotted tightly inside protons and neutrons by the strongest force in nature. A restless sea of gluons whose ceaseless activity shows up to gravity as mass and, by extension, shows up to you as weight. Start with the building blocks you were taught, protons and neutrons in the nucleus, electrons in their cloud, and then peel one layer deeper. Each proton or neutron is a tiny, thrumming composite, 3 lightweight quarks darting within a storm of gluon fields. If you could put the quarks on a scale by themselves, they would barely register. The two kinds that dominate ordinary matter are so light that their combined rest masses add up to only a few % of a proton's heft. Where then does nearly all the mass come from? From motion and binding. The quarks are confined by the strong force, and gluons, the carriers of that force, fill the proton with energy in the form of fields and fleeting quark-antiquark pairs that flare up and fade inside. Mass, as Einstein taught, is another way of counting energy. Trap enough energy in a small volume, and the world treats that trap as heavy. The strong force is unusual in a way that matters for your intuition. Unlike the electric force, which weakens as charges move apart, the strong force grows stubborn at larger distances, pulling quarks together with something like a spring that tightens the more you stretch it. Try to tear a quark from a proton, and the energy you pour in doesn't give you a loose quark. It snaps the string and conjures a new pair from the field, binding again into new particles. This property, confinement, means the inside of a proton is never quiet. Quarks ricochet with near-light speed. Gluon fields knot and unknot. and the swarm constantly reshuffles who carries momentum at any instant. That bustle is what your bathroom scale reads. It's also why you cannot point to a single ingredient and say, that is the mass. What you feel is the collective effect of motion and fields in balance. The idea isn't just a neat story. It's been hammered into shape by experiment and heavy computation. Smash protons at high speed and sift the spray, and you discover that a proton's innards are not 3 marbles, but a crowd of partons, quarks, and gluons, each taking a share of the momentum. Tune your probe's resolution and the shares change, revealing the field's life at different scales. On the theory side, physicists discretize space into a fine grid and simulate the strong force. Directly, lattice quantum chromodynamics is the mouthful, and from that brute force approach, the mass of the proton and neutron falls out within a few % of what we measure in real life. The match isn't an accident. It's a sign that the mass you live with day to day is a property of the strong interaction itself, not something bolted on from outside. Even a striking subtlety follows. Imagine turning off the mechanism that gives elementary particles their tiny rest masses. For the lightest quarks, the proton would still be heavy because the strong force would keep the energy inside high. In that sense, the Higgs field gives quarks and electrons their baseline non-zero masses. Electrons need that mass for chemistry to have shape, but the lion's share of the mass of your body and your chair and your city comes from the dynamics of gluons inside nucleons, not from the bare masses the Higgs supplies. You can see how decisive this is by doing a simple budget. Add up the masses of the electrons in a typical atom and you get less than 1%. Add the bare masses of the quarks inside the nucleus and you only climb a sliver more. The rest is binding energy, kinetic energy, and the intricate pressure of the gluon field. Even inside the nucleus, there's a second layer of bookkeeping, the nuclear binding that makes whole atoms lighter than the sum of their separated nucleons. But that reduction is small compared to the mass already created by the strong force inside each proton and neutron. If you picture mass as a ledger, almost every gram in your world is paid for by gluon activity. This can sound abstract until you realize how many empirical hooks hold it up. High-energy experiments map out how much of a proton's momentum is carried by quarks versus gluons at different scales. The answer includes a substantial gluon share that grows as you zoom in, consistent with the notion that gluon fields and flickering quark pairs fill the interior. Deep inside the math, there's also a feature called a scale anomaly. Roughly, the strong force refuses to be the same at every scale, which allows a particle with massless constituents to nonetheless acquire a definite mass. You don't need the equations to appreciate the moral. The field writes the heft. And because mass is just energy in a tight loop, it carries other consequences. Compress ordinary matter and you're pushing against the internal pressure of these fields. Heat it enough in a collider and you can briefly melt nucleons into a quark-gluon plasma, a fluid where quarks roam and gluons stream without confinement, like a rewind to the first microseconds after the Big Bang. Cool it again and the fields reconfine and the familiar masses reappear. There's humility in this picture, but there's also usefulness. In astrophysics, the same strong force that endows protons with mass underpins the stiffness of neutron-star matter. In technology, the nuclei you split or fuse in reactors release energy by rearranging binding, a small echo of the larger energy already bound inside each nucleon. Even your sense of everyday solidity, tables resisting elbows, stones resisting shovels, traces back to electrons for structure, but to nucleon mass for sheer inertia, and that mass is mostly a gluon story. Hold this as you move through your day. Your body is not a sack of tiny billiard balls that happen to be heavy. It is a lattice of atoms whose nuclei are compact storms, and what weighs you to the ground is the cost of containing those storms. It's tempting to ask what would happen if the strong force were weaker or stronger. Shift it down and protons and neutrons would be lighter. Nuclear binding would falter, and the periodic table might collapse into a sparse set of unstable curiosities. Shift it up, and the fields would clamp tighter. Masses would rise, and stars would burn differently, or not at all. In other words, your existence as you know it threads a narrow channel carved by this force. The quieter lesson is about where to look when you want explanations to go deep. Mass feels so solid that it invites a solid cause, but nature answers with activity, motion, fields, confinement, constant exchange, process, not substance. That answer can change how you hold the world. The weight in your palm is a history of interactions stabilized into a particle that endures. The chair under you is a frozen bill from the strong force, paid every moment in the language of energy that can neither vanish nor be perfectly still. Tonight, if you want a different kind of comfort, let this thought settle. You are carried through life by glue that is not sticky to touch, a glue of fields that binds quarks and, by binding them, creates almost all the mass you have, your steps, your sleep, the gravity that keeps you home. They all lean on a storm so small you will never see it, and so steadfast you cannot live without it. Proof that sometimes the heaviest things in your life are made of motion you can't feel and energy you can only imagine, holding everything together from the inside. Particles are ripples in fields, not tiny marbles. Touch the air in front of you and try to feel what isn't there, then let a quieter idea settle. The most faithful picture we have says the world is not built from little billiard balls, but from continuous fields that fill all of space. And what we call particles are localized ripples, brief, countable packets of disturbance, riding those fields the way a single pop travels through a sheet of bubble wrap. Once you switch your mental furniture from marbles to fields, a surprising number of puzzles rearrange themselves into something simple enough to live with. Start with the cast. There is an electromagnetic field spread everywhere, and when it ripples in a particular quantized way, you meet a photon. There is an electron field, and a compact, stable ripple in it is what you call an electron. Quark fields ripple inside protons and neutrons. Neutrino fields whisper across the cosmos. Even the carriers of certain forces, gluons, and the heavy messengers of the weak interaction, are themselves ripples in their own fields. The reason particle survives in our language is that detectors don't draw sine waves. They click. A camera's sensor, a Geiger counter, a photodiode, a piece of photographic film, all the old and new instruments register energy in lumps. Because a field's ripple at the right frequency and intensity cannot be absorbed in fractions smaller than a single quantum, the field delivers a minimal packet and the material responds with a discrete act, a dot, a spark, a mark. That dot tempts you to imagine a tiny pebble arrived. The field view says instead that a wave packet, localized enough to be caught here rather than there, has delivered its whole byte in one go. This shift helps you square two behaviors that seem incompatible when you cling to marbles. A ripple can spread and interfere with itself. Two paths can add or cancel, so before a measurement you must allow the possibility to occupy more than one route at once. Yet when the ripple finally couples its energy into a detector or an atom, the story ends with a single, definite spot, because the energy comes in whole quanta. There is no need to decide whether the world is really a wave or a particle. You are dealing with fields whose excitations behave as waves when they travel and as particles when they exchange their energy. The field picture also explains a deep sameness that marbles struggle with. Every electron you have ever met is indistinguishable from every other, not because the universe runs a perfect factory, but because there is only one electron field, and each electron is the same pattern of ripple in that same medium. That is why electrons share a mass and charge without exceptions, why they obey the same exclusion rule that keeps two from collapsing into identical motion inside an atom, and why light quanta, ripples in the electromagnetic field, can pile up without limit in a laser beam. Identity comes from the field, statistics come from the kind of field, variety comes from how the ripples arrange themselves. Even what you call mass fits more cleanly here. An electron's rest mass is not a marble's heft, but a property of its field, a measure of how the ripple resists being accelerated and how it trades energy with a background field that permeates space. The heavy messengers of the weak interaction carry mass for related reasons, while the massless photons field allows ripples that never slow down. Forces become less mysterious too. Two charged objects do not lob invisible marbles at each other across a gap. The electromagnetic field they both live in has a shape set by their charges, and that shape tells each object how to move. When the arrangement changes, disturbances in the field propagate outward at finite speed as light. In the strong interaction that binds quarks inside protons and neutrons, the relevant field behaves more stubbornly. Its ripples tug on each other, knotting energy so tightly that quarks can't wander off alone. And the bound energy inside that tiny volume is what shows up as most of the mass of ordinary matter. You don't need that inner storm for today's lesson. It's enough to feel how the field view replaces action at a distance with a local story. Things move because the field at their location pushes or pulls, and the field changes because nearby sources or ripples have reshaped it a moment earlier. Ask where this meets your senses, and the answer is everywhere, once you're shown how to look. The beam in a laser pointer is a disciplined parade of electromagnetic ripples. The track of a charged particle in a cloud chamber is not a marble carving a groove, but a field excitation nudging molecules into chains of drops along its path. The flashes in a particle detector are not tiny stones hitting a wall, but energy packets collapsing into a shower of new field ripples as a violent excitation relaxes into many calmer ones. The color of a leaf or a shirt comes from how electrons, ripples of one field, are allowed to dance with light, ripples of another, only at certain frequencies that a material's structure prefers. Even the notion of a vacuum softens. Empty space in this view is the field state with no ripples you can capture as particles, not a stage with nothing on it. And when you add energy in the right place, you lift the field into a configuration that behaves like a particle in motion. If you want a feel for locality without math, think about a stadium crowd doing the wave. The wave is not a thing that travels. It is a coordinated pattern, people standing and sitting, that moves and carries energy and information without any one person going around the stadium. A field is like that crowd extended across space. A particle is the minimal transferable packet of that organized motion. Interactions are places where two patterns overlap and exchange energy. The image is imperfect, but it beats a pocketful of pebbles when you need to explain why ripples can pass through each other and emerge unchanged, why they can cancel or reinforce, why they deposit energy discretely, and why two of the same kind can be genuinely identical without tracking serial numbers. The field language also untangles why measurements are such special moments. A detector is not a passive eye. It is a system designed to couple strongly to a particular field at a particular energy. When the incoming ripple's chance of coupling here is large, the detector absorbs the packet and something macroscopic changes. An electron is freed in silicon, a crystal flashes, a wire registers current, leaving behind a record we can't miss. Before that coupling happens, the ripple's possibilities spread according to the field's rules. After it, the field in that region has given up a whole quantum, and the remaining possibilities reshuffle in an instant because the boundary conditions that define the field have changed. You don't have to invoke intention or magic. The click is what it looks like when a field trades a whole packet of energy with a system large enough to keep score. This way of thinking isn't just philosophically tidy. It pays rent. It told engineers how to build transistors that rely on the controlled presence and absence of electrons in a solid's field. It told chemists why only certain frequencies of light trigger reactions. It told astronomers how to read the spectrum of distant stars as a ledger of field ripples absorbed and emitted in their atmospheres. It told medical physicists how to create and detect gamma rays for imaging. It told material scientists how to coax superconductors into behaviors that feel like levitation. Push the same logic abroad and you get gravitational ripples, waves in space-time itself, arriving from colliding black holes, detected as minute stretches and squeezes in laser arms, thousands of times smaller than a proton's width. Each success returns the same moral. Once you treat particles as the quanta of fields, the world's most surprising effects feel like straight lines, not rabbit holes. For your own understanding, the reward is a gentler, more accurate picture to carry into quiet moments. You are not a bag of tiny stones. You are woven from fields whose ripples hold steady shapes at human temperatures and pressures. The chair is not a pile of beads. It is a structured place where certain field excitations are allowed and others are forbidden, and the resistance you feel when you push on it is the sum of many local field responses, not the jostle of solitary marbles. Light from a lamp, sound from a string converted to electric over a cable, the stability of an atom, the spark on a winter doorknob. They are all conversations between fields expressed as packets and patterns. Hold this and the world grows less cluttered. You need fewer ad hoc rules, fewer as-if stories, fewer exceptions. There are fields, there are their excitations, and there are the ways those excitations meet and trade energy. And when you lie back tonight and let the room dim, you can allow a quieter comfort in. The smallest things that make you are not hard seeds rattling in a box, but organized motions in continuous media that never run out of space. The steadiness you feel from your body and your books is the poise of those motions. And every time a detector clicks or a spark jumps, it isn't a marble hitting a wall, but a ripple arriving at the end of its journey. laying down its packet and vanishing into the same fields that fill the dark around you. You share atoms with everyone who ever lived. Take a slow breath and picture it doing something quietly outrageous. Some of the oxygen rushing into your lungs has almost certainly been inside other lungs before. Farmers, sailors, kings, children at school, singers on stage, and the water that softens your mouth has flowed through strangers and mammoths and fern forests, because you do not own your atoms so much as borrow them from a restless common pool that the planet keeps mixing and lending. Over a lifetime, you will trade most of your body's atoms with the world many times, so that by simple arithmetic and steady circulation, you share matter with virtually everyone who ever lived. Start with the scale you can hold in your head. A single easy breath contains on the order of tens of billions of air molecules, and the atmosphere itself holds a number so large it makes names feel silly. When the winds mix, which they do quickly in your part of the sky and more slowly around the globe, the molecules from any one breath distribute widely, and the next time you inhale, you pull in a few strays from innumerable past exhalations, whether or not you like the company. This isn't folklore. It falls out of the way, gases spread and dilute. Each exhale is a small splash in a huge reservoir, but the reservoir is old and your sampling is relentless. Tens of thousands of breaths each day for the years you are here. So the expectation that you will encounter molecules that once left Shakespeare, a shepherd on the Anatolian steppe, or a fisherman on the Pearl River isn't romantic flourish. It's the natural consequence of vast numbers and continual mixing. Water tells the same story with different pauses. In a single glass, there are more water molecules than there are stars in the observable sky, and those molecules circulate among oceans, rivers, clouds, soil, and living things on timescales that range from days to millennia. Droplets evaporate, condense, fall, seep, freeze, melt, and evaporate again. Roots pull them up, cells stitch them into sugars, animals drink, sweat, and urinate. Ice locks them away for a season or an age and returns them later. Drink now, and you are swallowing a solution that, by sheer combinatorics, almost certainly includes molecules that splashed Roman bathhouses, pooled in a cave beside Paleolithic fires, or coursed through the sap of trees felled for the first boats. Food completes the exchange. The carbon in your muscles and brain spent earlier lives in leaves and grain, in insects and cattle, in people whose bodies decayed into soil that fed the next harvest. The nitrogen in your proteins was fixed from air by microbes or machines, passed into plants, moved into animals, and now sits in your cells until it departs again by breath and waste. Even the calcium in your bones is not a birthright. Your skeleton is under quiet renovation all the time, old mineral dissolved and replaced, so that over a decade or two, most of the atoms in it have been traded for new ones drawn from milk, greens, fish, or pills. Atoms that once were rock, then river, then plant or animal, then you. Put the pieces together and the picture is plain. The atoms in a typical adult number in the trillions of trillions, and across the decades, nearly all of them turn over. The biosphere is large but finite. The atmospheric and water reservoirs are huge mixers. The human past is long and populous. Multiply these facts and the odds that you now carry at least some atoms that once belonged to any given historical person. Climb from maybe to very likely. And the odds that you share atoms with countless unnamed people become overwhelming. There are honest caveats that keep the idea disciplined. Some atoms are sequestered for a while in limestone, deep aquifers, or polar ice. Some human remains were burned or buried in ways that slowed their return to circulation. And what you share from any one individual is an infinitesimal fraction, chemically indistinguishable from identical atoms from everywhere else. But the point is not to imagine a ghostly transplant. It is to understand a civic physics of matter. Atoms are durable on human timescales. They are swapped through breathing, drinking, eating, sweating, shedding skin, and going to the bathroom. The planet's air and water and soil are the commons across which those trades happen, with winds, rivers, and roots as brokers. And the mathematics of mixing says that Given enough time and breaths and meals, the reach of those trades spans cultures and centuries. If you want a feel for it without equations, try 2 home experiments in imagination. First, the breath problem. Picture the entire atmosphere as a vast lake of marbles and your exhale as a ladleful poured in. Stir long enough and then scoop another ladle. Because the lake is ancient and you are scooping constantly, some marbles you gather now almost certainly came from countless ladles before yours, including those tipped by people you have only read about. Second, the water problem. Fill a glass from the tap and remember that every raindrop has a story of earlier cycles. The odds are excellent that a handful of molecules in that glass passed through Cleopatra's veins, or a poet's tear, or a farmer's sweat. You cannot tag them. The glass does not taste different, but the statistics are patient and, over the long run, mercilessly inclusive. If this leaves you with a soft unease, am I diluted by strangers? Let it flip into a steadier comfort. Identity in biology isn't about owning particular atoms. It's about holding particular patterns. Your body is a choreography that recruits atoms, keeps them busy for a while, and lets them go. Your sense of self rides on the arrangement and the traffic, not on the serial numbers of the parts. That understanding has practical bite. It explains why diet matters quickly. New atoms arrive and become you within hours and days. Why hydration and air quality have near-term effects. Why bone health is a long game of supply and turnover. And why pollution lingers by entering loops that feed it back to us. It also reframes responsibility. The emissions you release, the chemicals you pour, the care you take with water and soil do not vanish. They enter the same mixers that supply your next meal and your neighbor's breath. And it warms history in an unexpected way. Think of the planet not just as a stage for separate lives, but as a slow, shared metabolism. The writers and builders and nameless workers of the past are part of what you are made from in the most literal sense, and you, in time, will return your atoms to the stream for others to borrow. Tonight, when you inhale before sleep, you can hold this without drama. In that breath, and in the sip of water on your nightstand, are specks of the same world that carried emperors and midwives, artists and sailors, grief and laughter. What makes you you is the brief, brilliant way your body arranges those borrowed pieces. And what steadies you is the knowledge that when the arrangement changes, the pieces do not fall into nothing but back into the patient circuits of air, water, soil, and life. Plants use quantum tricks to move sunlight efficiently. Turn a leaf toward the sun in your mind and set aside the idea that it simply soaks up light. What actually happens is a precise relay race that begins when a pigment catches a photon and turns it into a tiny packet of excitation, an exciton that must find its way across a crowded, nanoscopic forest to the reaction center before it fades. And the surprise is that the exciton doesn't plod like a drunk walker from molecule to molecule, but, for a brief, crucial moment, spreads as a coordinated quantum wave so it can sample many routes at once and let interference steer it toward a fast exit. A trick that helps plants move sunlight with striking efficiency in the first instance of photosynthesis. The layout is deliberate down to angstroms in antenna. Complexes. Think of the green protein scaffolds studded with chlorophylls. In your houseplant or the bacteriochlorophyll, networks in purple bacteria. Pigments are held at just so distances and angles, so that energy levels form a gentle downhill funnel, and couplings between neighbors are strong enough that when one pigment absorbs light, its excitation is not locked to that site, but shared across several, like a cord ringing across a few strings at once. In this regime, the excitation behaves as a wave packet that explores multiple neighbor-to-neighbor paths simultaneously, which means it can avoid dead ends and bottlenecks that would trap a purely random hopper. The leaf isn't a cryogenic lab though. It runs warm, wet, and noisy. And here is the second, subtler trick. A small amount of environmental jostle actually helps. If the network were perfectly coherent forever, the wave could interfere with itself in unhelpful ways and localize, stuck ringing in a cul-de-sac. If the environment were too rough, coherence would die immediately, and the motion would revert to slow diffusion. Plants operate in a sweet spot where fleeting quantum coherence, lasting for tens to hundreds of femtoseconds, interleaves with just enough defacing from the protein and water around the pigments to nudge the excitant out of traps. Researchers sometimes call this balance environment-assisted transport. Noise, usually the enemy in machines, becomes a guide that keeps the quantum walk moving. You don't have to take that on faith. Ultrafast spectroscopy can watch the handoff. In two-dimensional electronic spectroscopy, a train of femtosecond laser pulses tags the excitation and measures how it moves. In model systems like the FMO complex from green sulfur bacteria, and in higher plant antennas such as LHCII, those measurements show oscillatory fingerprints that persist long enough at room temperature to argue that some coherent sharing survives in working conditions. And the net result lines up with kinetics. Energy reaches the reaction center in a handful of 100 femtosecond to picosecond steps, with a quantum yield near unity for the initial charge separation event, meaning that once light is caught, the relay almost always delivers it to the place where chemistry begins. Honest nuance matters. Scientists still debate how much of those oscillations reflect truly electronic coherence versus vibrations of the pigment protein scaffold that march in step with the excitant and keep pathways aligned. Either way, the practical picture is robust. Correlated motion plus tuned noise beat naive hopping in the messy living interior of a leaf. The architecture that makes this possible is actively managed, not static wallpaper. Under gentle light, plants keep their antenna arrays open and their energy funnels steep. When sunlight blazes and reaction centers risk overload, the same proteins shift gears. Non-photochemical quenching routes spill over energy into harmless heat to protect the chemistry downstream from damage, a proof that the network is not only efficient but adaptable. And scale puts the idea in perspective. The overall conversion of sunlight into sugars across an entire plant tops out at only a few percent because there are many later steps with losses. But the transfer stage, the one that moves the exciton to the reaction center, is so nearly lossless that it would embarrass many human devices. That matters for technology. Engineers trying to build better solar cells or artificial leaves have learned that copying nature's exact pigments is not necessary. What pays off is copying the principles. Arrange absorbers so their energies step downhill, couple neighbors strongly enough to allow brief coherence, and welcome a touch of tailored disorder so that noise shakes excitations loose from traps instead of smearing them into oblivion. In organic photovoltaics and excitonic circuits, designers now tune molecular packing and vibronic couplings to recreate this middle ground. In quantum information and sensing, the leaf's lesson is even broader. Sometimes you design with the environment instead of fighting it, letting specific vibrations or temperature fluctuations play the role of quiet helpers that move probability in your favor. For you as a curious observer, the shift is simple and deep. A leaf is not just a green surface. It is a quantum-optimized network running at body temperature conditions, turning sunlight into chemical potential by letting waves wander wisely for a blink, and then locking that wander into charges at exactly the right spot. If you go back to the sunlit window and really look, you can read the choreography. Pigments absorbing across a spread of colors to keep the catch wide. Protein scaffolds acting like springy trellises that tilt energy levels and modulate couplings. Reaction centers poised to seize the arriving packet and split it into charges before decoherence can waste it. Safety valves opening when the flux gets rough. And you can let that picture teach a gentler mental habit. Efficiency is not always about sterility or absolute control. Often it's about tuning the mess, about finding a regime where a little coherence and a little noise weave together into flow. The next time you pass a tree and the leaves are clicking softly in wind, consider the quieter click you cannot hear. Excitations leaving pigments in waves, sliding along a microscopic landscape that was sculpted by evolution to make chance work for it, and arriving, almost without fail, at the place where light becomes life. You can hear the difference between hot and cold water. Lean closer to the sink and try a small experiment with your ears. Pour cold water into a glass, then pour hot, and you'll notice, without peeking, that the second pour sounds finer, hissier, a little more like rain on leaves, while the first is rounder and more glug. And that simple difference hides a whole lesson about how temperature tunes matter and how your brain reads physics as music. What you're really hearing is a change in the way water flows, breaks, and traps air. Because warming a liquid quietly lowers its resistance to motion and softens the skin that holds its surface together. So the falling sheet turns more turbulent and fractures into smaller, quicker bubbles that ring at higher notes than the larger, Slower bubbles favored by cold water. Start with flow. Cold water is thicker in the sense that its molecules cling to one another more strongly. So for the same faucet opening and height, it tends to pour as a smoother ribbon that resists shredding. Warm the water and that internal stickiness eases. The stream destabilizes earlier, and the falling sheet frays into ripples and filaments that flicker faster when they hit the glass, adding a fine hiss to the soundtrack. Then layer in the surface itself. The invisible tension at the boundary between air and water acts like a stretched film. Cold water has a tighter film that prefers to hold shapes together. So when air gets trapped, it tends to form slightly larger cavities, while hot water's looser film allows quick pinch-offs into smaller air pockets. You don't need equations to feel the consequence. Small trapped bubbles ring at higher pitches than big ones, the way a tiny bell tings brighter than a gong. Those rings are not metaphor. When a droplet plunges under or a sheet crashes into the rising water, pockets of air are captured and squeezed. The pressure difference makes each pocket expand and contract for a few beats before it dissolves. And those oscillations radiate sound into the glass in your kitchen. Change the typical bubble size and you shift the band of notes you'll hear. Temperature tugs a third thread too. Warm water carries less dissolved gas than cold, so as it leaves the faucet and smacks a surface, it is a little more prone to shedding the gas that remains, seeding more tiny bubbles. Cold water arrives with more gas in solution, but because its surface and internal stickiness are stronger, it favors fewer, larger cavities when those bubbles finally appear. Together, those differences sculpt what acousticians call the timbre, the blend of hiss, tinkle, and gurgle that your ear sorts without words. Even the container joins the duet. A thin glass sings along with higher frequencies, while a heavy mug dampens them. A metal sink splashes brighter than a plastic basin. Fill depth changes the tone because deeper water cushions impacts and shifts where bubbles form. But through all these variations, the hot-cold signature usually survives. Hot water brightens the treble. Cold water fattens the bass. Your brain, for its part, is a brilliant statistician with no math on paper. It averages thousands of microscopic events over a second. The rate at which threads of water break, the distribution of bubble sizes, the way high frequencies rise and fall, and turns that into a single impression you can use immediately. That sounded hot. That sounded cold. Studies that blindfold listeners or feed them recordings show that even untrained people can pick the hot pour above chance. And once you practice, the skill becomes uncannily reliable because you're really classifying physics, not memorizing trivia. There are easy ways to test and feel each ingredient. If you pour from higher up so the jet lands harder, you force more breakup in both hot and cold streams, and both grow brighter, yet the hot stream still leads in hiss because its surface lets go more easily. If you pour down the side of the glass so the sheet slides gently, you muffle the crash and shrink the bubble orchestra, and the sounds of hot and cold converge a bit. Proof that the difference comes from how bubbles are made. If you add a drop of dish soap to cold water, you reduce surface tension and for a moment, give it a hot water sparkle even though the temperature hasn't changed, a kitchen-friendly hint that the skin of the liquid is one of the main dials. None of this means hot water is universally higher pitched under all conditions. Pour very slowly into a deep, already filled vessel and geometry can dominate. Use very hot water and steam adds whispering tones of its own. Pour onto ice and the crash chorus overwhelms everything. But as a rule of thumb that survives most ordinary pours from a tap, warmer means hissier and brighter because it flows more freely and breaks into smaller, faster ringing structures. If you like numbers without symbols, hold only this. A small bubble vibrates more times per second than a big one, and warm water tends to make more small ones. A thicker liquid resists quick, fine motion, and cold water is thicker. A tighter surface prefers big, rounded shapes, and cold water's surface is tighter. Your ear can't pass viscosity, tension, or dissolved gas, but it can pass their consequences, and it has been doing so since childhood in every bath, kettle, and creek, storing an unconscious map that guides judgments as mundane as this tea is still too hot, and as practical as the pasta water is about to roll. There's a deeper teaching within the party trick. You learn that sound is a biography of events you can't see. The scratch in a violin string telling you about rosin and pressure, a car tire whispering road texture, a coffee pour announcing grind and height. Your faucet becomes another narrator, translating molecular properties into audible textures. You also learn that your senses like to cooperate. If you close your eyes, your hearing sharpens. If you watch the stream while you listen, you'll start to match hiss to fine spray, glug to larger slugs of air, and the knowledge will stick. And you learn, perhaps most usefully, that everyday phenomena have layered causes. No single villain, no single hero, but a chorus. Internal friction, surface skin, trapped air, container shape, or sharing the job of making a sound. That habit of mind serves beyond the sink. Next time you step outside after rain and hear the difference between drizzle on leaves and drops in gutters, or notice how boiling becomes a deeper roar as bubbles grow, you'll know what knob's reality is turning. And tonight, if you pour a glass of water in a quiet room, you can let your ear do what it's built for. Catch the faint treble of warmth or the rounder voice of cold, and take a small pleasure in the fact that you just read temperature with no thermometer at all. Only a stream, a vessel, a handful of bubbles too small to see, and a brain that turns physics into music and back again without asking your permission. Space can expand faster than light without breaking causality. Look up at the night and try a sentence that sounds like cheating. Parts of the universe are moving away from us faster than light, and nothing illegal is happening, because it isn't galaxies sprinting through space that outrun light. It's space itself stretching in between, and that distinction is what keeps causality safe while letting the cosmos grow with breathtaking speed. Start with what's local and sure. Special relativity lays down a firm rule inside any small neighborhood. No object or signal can outrun a light beam measured by a nearby clock. General relativity keeps that rule, but adds a new freedom at grand scales. The metric, the ruler we use to measure distances, can change with time. When the ruler stretches, two faraway points can see their separation increase, even if neither is racing through its own patch of space. Cosmologists keep score with a scale factor that swells as the universe ages. Multiply distances by that factor, and you get what's called the recession of galaxies. Near us, the recession is gentle. Double your distance and, roughly, you double the recession rate. A relationship discovered a century ago when astronomers noticed that distant galaxies' light is stretched redder in proportion to how far they are. Push far enough out though, and the product of distance times expansion rate can exceed the speed of light. That's the headline. There exist galaxies whose proper distance from us grows faster than any flash could bridge. It sounds like a paradox until you sit with the geometry. The cosmic speed limit is local. It bans a rocket from overtaking a photon in its own neighborhood. It does not forbid the distance between two far-off neighborhoods from increasing at whatever rate the changing metric delivers. Imagine a moving walkway running between you and a friend. Neither of you runs. The walkway itself lengthens. If it lengthens quickly enough, the gap between you grows faster than your fastest sprint, even though no feet violate a rule. In the universe, the walkway is not a machine, of course. It's the dynamical fabric of space-time responding to its contents. Dark energy, the name we give to the smooth energy density that today drives an accelerated expansion, acts like negative pressure, urging the growth of that scale factor faster and faster on the largest scales. This is why we talk about horizons. The observable universe is the region from which light has had time to reach us since the hot beginning. Because the ruler has been stretching the whole time, that region is far larger in present-day size than the light-traveled distance you'd naively compute. The Hubble radius marks where, right now, recession creeps to the speed of light. Objects beyond it recede superluminally today. Then there's the event horizon, a softer boundary defined by the future. Beyond it sit places from which light launched today will never reach us. Not because light is lazy, but because the road under it keeps extending faster than the light can close the gap. None of these horizons are walls. Photons already en route from just beyond the Hubble radius can and do arrive, stretched and dimmed, but they are faithful bookkeeping devices. They tell you what can ever talk to what if the expansion history keeps its course. You may ask, if space can stretch this way, why don't we and our buildings and our star systems swell like taffy? Gravity and other local forces answer. The expansion only rules where the average pull of matter is so weak that the overall flow wins. Within the Milky Way and the small cloud of galaxies bound to it, mutual gravity dominates. Atoms are held by electromagnetism, rocks by chemical bonds, people by solid floors. Expansion shows its hand only across scales where no tether wins. That is why the Andromeda Galaxy is on a slow collision path with us, even as more distant galaxies flee. Local gravity trumps the background current, but farther out the current is stronger than any tie. The early universe took this logic to an extreme during a brief episode called inflation, when the scale factor ballooned nearly exponentially. Space doubled and doubled again on timescales far shorter than a blink, so that regions once in easy contact were pulled apart faster than light could knit them together. This didn't break causality. It made the sky smooth by stretching one nearly uniform patch to cosmic size, and it left faint fingerprints, tiny ripples in temperature across the microwave background and in the distribution of galaxies that we can still read. Inflation's job, if you like, was to hand off a big, even canvas to the later, slower expansion that we measure today. Observationally, the story hangs together in multiple ways. The light from faraway galaxies is redshifted, not because they are plowing through a stationary medium, but because the waves themselves are stretched while crossing an expanding stage. Distant supernovae look a touch dimmer than they would in a steady expansion, a clue that the growth is accelerating rather than coasting. The afterglow of the hot beginning arrives from all directions at almost the same temperature, which makes sense if distant regions were once near enough to share properties before expansion heaved them apart. Catalogues of galaxies reveal a faint, standard ruler imprinted by ancient sound waves in the early plasma. Measuring that ruler at different redshifts is like checking mile markers on an unfamiliar highway, and the mile markers line up with a universe whose distances swell faster and faster in late times. Each piece is a partial story. Together, they sketch the same geometry, a metric that grows and, on large scales, can separate places faster than light can bridge, without allowing anyone to signal backward in time. If you want a fingerhold on causality, think in cones. Every event in space-time has a light cone, the set of places light can reach from there, and the set that could have reached it. Expansion tilts and narrows those cones across the map, but it never lets a message climb outside its local cone. You cannot use the growth of space to send a warning to your own past. You cannot arrange a clever relay of receding galaxies to game the limit. All go-betweens are bound locally by the same speed law, and the large-scale bookkeeping of distances respects those local contracts. What does this change in how you hold the night? It lets you accept two honest truths without tension. First, there are galaxies we will never see, and others we see now that will slide beyond our ability to contact no matter how long we wait. Because the river under every photon will keep lengthening in certain directions faster than strokes can overcome. Second, within every ship, every lab, every solar system, light remains the tightest leash on cause and effect. Our neighborhood stays intelligible, even as the map beyond our neighborhood stretches. There is a quiet, practical wisdom here for your imagination. When you hear faster than light, ask where, through space or of space. When you meet a redshift, remember it is time's handwriting on a wave. When you think about the future, picture the local groups sailing in widening emptiness, islands of matter drifting apart while their own shores hold. And when you close your eyes, let this paradox that isn't a paradox slow your thoughts. The universe can expand faster than any messenger can run, and still no message breaks its promise. Growth and law live side by side, and the stars you see tonight are part of a story in which space itself makes the distance, patiently and legally, while light does what it always does, carry news as far as the rules allow. Then hand the rest to your wondering. Lasers can slow atoms to a crawl. Forget the sci-fi ray gun that blasts things faster. Here's the quieter truth that feels like a magic trick you can audit. Aim carefully tuned laser light at a cloud of hot atoms and you can make them slow down. Not by shoving them with brute force, but by letting them absorb little nudges only when they're moving the wrong way. Until their frantic thermal motion calms to a crawl, you could almost outrun with a garden snail. The key is a simple pairing of two everyday ideas. A moving siren changes pitch as it passes, and a stream of tiny taps can break a wheel without cracking it. Atoms have favorite colors of light they'll absorb. If you tune your laser slightly redder than that favorite, a stationary atom largely ignores it. But an atom flying toward the light sees the wave blue shifted into its sweet spot and grabs a photon. Each absorbed photon carries a whisper of momentum and gives the atom a kick opposite its motion. A moment later, the atom spits the energy back out as a photon in a random direction, which averages to almost no push over many cycles. Net effect: one directional nudge toward rest. repeated tens of thousands of times per second. Put a laser along each axis, left, right, up, down, forward, back, and any atom that tries to slip away meets a headwind of light. This arrangement is nicknamed optical molasses, and the name fits. With the right detuning and intensity, the cloud's jitter dies down until the atoms drift as if moving through syrup, their speeds falling from hundreds of meters per second to mere centimeters or millimeters per second. There are practical dial turns behind the poetry. Because a slowing atom quickly slips out of resonance, you need a way to keep the light looking just right as it breaks. One method is a Zeeman slower, a tube whose magnetic field changes along its length, so the atom's internal levels shift in step, making the light feel resonant all the way down the ramp. To gather and hold the cooled atoms in one place, experimenters add a faint, spatially varying magnetic field to their laser beams. Now the light not only damps motion, but also provides a gentle restoring push toward the center. This contraption, 3 orthogonal pairs of circularly polarized beams plus a field gradient, forms a magneto-optical trap, a kind of invisible hand that corrals 1 million or 1 billion atoms into a glowing thimble in high vacuum. There's a temperature floor set by the very process that cools. As atoms bounce photons, the randomness of re-emitted light jitter heats them a little. So the basic Doppler technique stalls at an ultra-cold but not absolute limit. Cleverty doesn't end there. By sculpting the polarization of the light into a faint landscape, you can make atoms repeatedly climb small hills of internal energy and lose kinetic energy on each ascent, a mechanism nicknamed Sisyphus cooling. Combine this with molasses, and the cloud can slide below the simple Doppler limit into the realm of microkelvin, where thermal speeds are so low that a gentle drift takes a whole second to cross a millimeter. At that point, even the pushover recoil from a single photon matters, one last fundamental jostle that sets the ultimate floor. If you want to go colder still, you can change tactics. Hold the atoms in a shallow light or magnetic bowl and start skimming off the fastest ones, letting the rest rethermalize at a lower temperature. Keep skimming and you push into nanokelvin territory, cold enough that a cloud of special atoms merges into a single quantum wave, a Bose-Einstein condensate that sloshes like syrup made of probability rather than points. But you don't need to chase that extreme to see why slowing atoms matters. With a molasses and trap routine, you can build clocks that count the rhythm of atoms with so little motion blur that they would lose or gain less than a second over the age of the universe. You can make matter wave interferometers that drop 2 paths of atoms side by side and read out gravity from the way the waves recombine, sensitive enough to map underground voids or track the slow swell of tides in Earth's crust. You can assemble arrays of single neutral atoms like checkers on an optical board, switch their interactions on with a pulse of light, and study magnetism, chemistry, or even perform logic for quantum computing, all while the atoms barely wander. Even chemistry looks different when the players crawl. At these temperatures, colliding atoms and molecules meet so gently that a handful of quantum pathways dominate, and reactions that would be a blur at room temperature unfold like a choreographed duet you can time resolve and control. None of this is easy in the lab. It takes lasers that are locked to their colors so tightly they hardly drift over a day, mirrors that hold alignment to hair-breadth tolerances across a meter, vacuum chambers that keep stray gas molecules at bay so the delicate cloud isn't kicked apart, and feedback loops that watch and correct the trap like a patient breathing coach. The power demands are modest. The demands on steadiness and cleanliness are not. Yet the principle stays human simple. Tailor the light so atoms only absorb when it helps them slow, and let spontaneity handle the bookkeeping of the re-emitted photons. If you want a kitchen table intuition, imagine a child running into a crowd where everyone holds out soft cushions. The child only collides when heading outward, not when turning back. So each bump steals a bit of speed without sending them flying in a new direction. Repeat this in 3 dimensions and the sprint turns to a stroll. And if there's a gentler lesson to carry beyond the hardware, it's that control can come from bias rather than brute force. You don't need to overpower an atom to tame it. You need to tune the environment so that every random act, on average, leans your way. Laser cooling turns noise into help, chaos into drag, and heat into stillness, by changing the rules about when interactions are allowed. The next time you see a laser pointer dot skitter across a wall, remember its quieter cousin in a physics lab. Beams you can't see, tuned a hair below resonance. bathing a tiny cloud until the atoms inside forget how to hurry. And in that calm, now slow enough to hold and weigh and count, they begin to tell you truths about time, gravity, and matter that were hidden when everything moved too fast. There are more possible chess games than atoms in the universe. Slide a pawn forward in your mind and feel the board breathe a little. Because with that small push, you've already chosen one branch from a forest so vast that the count of different games you could, in principle, play dwarfs the number of atoms in the observable universe. This isn't a slogan meant to impress dinner guests. It's a sober reminder of how fast possibilities multiply when choices stack, and it teaches you something practical about complexity, creativity, and why mastery in rich systems comes from guidance rather than brute force. Begin with the bare mechanics. From the starting position, White has 20 legal moves, and after each reply, the menu fans out again. The average number of legal moves available on a typical turn hovers around a few dozen, sometimes fewer in tight endgames, sometimes far more in wild middle games. If you imagine a game of modest length, say 40 moves per side, which is common in tournament play, and you pretend the branching stayed near that average, the tree of distinct move sequences explodes, first 20, then roughly 35 choices on many turns, then again and again, so that even if you round conservatively, the total number of different complete games reaches a 1 followed by about 120 zeros. That Shannon number, named for the engineer who formalized information theory, is not an exact census. No one can list them all. And many sequences would break rules like the threefold repetition draw or the 50-move rule, but it's a fair lower bound for how many legal game histories are available when you mix realistic lengths with ordinary branching. Compare that with the atoms in the part of the universe we can in principle observe, a number that experts estimate as a 1 with about 80 zeros, and you begin to see why more chess games than atoms is not hyperbole. The trick here is that you are comparing apples and forests. Atoms are physical constituents we can count in a volume. Games are sequences, and sequences grow combinatorially as soon as you allow many steps with many choices. If you change the question from distinct game histories to distinct board positions reachable under the rules, the count drops a lot. The estimates land somewhere around a 1 with 40 to 50 zeros, because different move orders often reach the same arrangement, and constraints like castling rights and en passant possibilities reduce duplicates. But even that smaller space is beyond any hope of brute force cataloging by a human mind. The core insight is not a number, but a shape. A game like chess grows outward like a branching coral with every ply, and the outer surface of that coral is so huge that, for all practical purposes, no two long journeys are the same. This is why novelty shows up in Grandmaster practice decade after decade, even when everyone has databases. Most recorded games share openings because those are safe harbors carved by collective experience. Yet once you sail past the bookline by move 12 or 20, you are nearly always on fresh ocean. There's an honest caveat that keeps the idea grounded. The statement refers to possible games, not sensible ones. Most sequences in that stupendous count are nonsense for strong play, blunders, repetitions, aimless shuffling, positions that any trained eye would reject at a glance. But that's part of the lesson. Interesting worlds often contain vastly more bad choices than good ones, and wisdom consists in pruning. Computers learned this the hard way. If a machine tried to evaluate every move sequence to the end, it would stall after a handful of turns. Instead, modern engines slice the tree with guidance, expanding likely lines and ignoring deserts, using fast evaluations to assign promise to positions and ruthlessly abandoning branches that look sterile or losing. Techniques with friendly names, search windows, pruning, transposition tables that remember positions reached by different move orders, are all ways of saying, in a world too large to see, remember and predict fully, direct your attention where it buys you understanding. You can feel this in your own games. When you study an opening, you're not trying to memorize a map to the horizon. You're trying to learn principles that reduce the meaningful choices. Control the center, coordinate your pieces, keep your king safer than theirs, so that from dozens of legal moves, only a sane handful remain. When you practice endgames, you're compressing vast possibility space into recognizable patterns. Lucina bridges, opposition in king and pawn endings, triangulation tricks that lose a tempo on purpose. The immensity behind those patterns is why the patterns matter. Another way to hold the claim is to think about information. A single full game record, move after move, carries far more information than a single snapshot of the pieces, because it includes history. Which pawn stepped 2 squares last turn? Whether a rook and king have moved before? Whether a threefold repetition is looming? The rules of chess make history matter, and history multiplies possibilities. In life, you do the same thing without naming it. You move from a photograph to a story, from a state to a path, and the count of distinct paths dwarfs the count of snapshots. That's the deeper moral of the number. Once paths matter, the tree of futures balloons. You might ask whether this claim cheapens other grand numbers, like those tossed around for Go. In that cousin board game, the space is even larger, with a typical branching factor, bigger still, and a grid that starts open instead of half occupied. But the comparison isn't a contest. It's a family resemblance. Both games prove the same point. Simple local rules can generate a universe of play that outruns naive enumeration, and that's why they hold attention for a lifetime. The physics metaphor that sometimes shows up, that this is bigger than the universe, isn't meant to confuse counts of matter with counts of stories. It's a reminder that combinatorics can outpace cosmology very quickly. You can bring this back to something you can use tomorrow. When you sit down at a board, you're choosing a path through a world where most branches lead to fog. Your job is not to fear the fog, but to learn the shapes of clearings. Often that means asking better questions, not what is the best move, as if one existed in isolation, but what matters here, which translates to what features of this position shrink my relevant options. Is the king unsafe? Are there weak squares that can't be defended? Are there tactical motifs, a pin, a fork, a discovered attack, that collapse the tree because only one move avoids disaster or converts advantage? Each identified feature is a pruning rule that shrinks more games than atoms, down to 3 ideas worth calculating. Engines do this with number crunching and heuristics. You do it with experience and a notebook. The immensity also explains why creativity never runs out. If 2 club players sit down after work, the chance that their game duplicates an ancient Grandmaster masterpiece move for move is effectively 0. The chance that their middle game reaches a position no human has ever visited is effectively 1. That shouldn't make you arrogant. It should make you curious. What new idea can you test today, knowing that the game's combinatorial generosity will grant you chances to be original, whether you ask for it or not? And what discipline can you bring to that originality so it isn't just noise? Finally, there's a gentler reflection beyond the board. The phrase "more games than atoms" wears a showman's coat, but underneath is a practical ethic for any field crowded with choice. You will not conquer the tree by looking everywhere. You will survive by learning where to look. Good openings in your work, solid middle games in your habits, accurate end games in your commitments. These are patterns that reduce the search while preserving freedom. That's what study is for, and why we keep returning to books, coaches, and our own errors, to carve sensible pathways through an otherwise ridiculous space. So the next time you touch a knight and feel the slight click of wood, pause for a heartbeat and notice the miracle hiding in that sound. A tiny decision that turns away from an astronomical count of other lives the game could have lived. You don't need to see those discarded branches to respect them. It is enough to know they are there and to take a quiet pride in the one you chose, played out on 64 squares, under a lamp on a good evening, when the world outside was large and you made it manageable by pattern, patience, and a willingness to think a few moves ahead. Your phone's camera can catch cosmic rays. Turn off the lights. Cover your phone's camera with a piece of thick black tape. Open a long exposure or dedicated cosmic app. And wait. Every so often, a frame that should be pure darkness will bloom with a sharp white streak or a tiny starburst. And in that quiet flash, your pocket computer has just felt a messenger from space, proof that your phone's camera can catch cosmic rays, not as a gimmick, but as a miniature solid-state detector reading the same physics that fills professional labs. What you're seeing isn't a primary cosmic ray. Those are mostly protons and heavier nuclei launched by violent astrophysical engines far beyond Earth. But a secondary, usually a muon, born high in the atmosphere when a primary smashes into air and makes a cascading air shower of short-lived particles. Pions decay into muons. Muons dive onward at nearly light speed. And because they interact weakly and live just long enough when time dilation lends them extra life, a flood of them reaches the ground. Roughly 1 per square centimeter per minute at sea level on average. Your phone's sensor is far smaller than a square centimeter and covered by glass, filters, and a lens stack. So the number you personally catch is modest, maybe a few in an evening if you're patient, and your app watches constantly. But when one passes through the silicon, it leaves a string of ionization that a camera chip can't tell from a burst of light, so a clean, covered frame suddenly sprouts a slash of saturated pixels, sometimes ruler straight and sometimes a short worm if a lower energy electron ricochets and changes direction. The underlying mechanism is delightfully simple. Each pixel is a tiny photodiode waiting to collect charge. Normally that charge comes from photons the lens focuses, but a charged particle can plow through the lattice and create electron hole pairs directly, dumping a packet of charge into many neighboring pixels as it slows. The chip's readout dutifully reports a bright track even though no light ever arrived. You can learn to read these events after a few tries. Hot pixels, manufacturing defects, or thermally noisy sites keep flaring in the same coordinates across many frames. Cosmic hits pop up in new places, overwhelmingly in a single frame or two. Readout streaks have the geometry of the sensor's scan and respect rows or columns. Muon tracks cut at arbitrary angles that don't care about the grid. Gamma rays and betas from natural radioactivity in the phone's materials or the room can create small, blobby splashes, useful to know but easy to confuse with the real prize, while the long, clean, almost ruler-straight diagonals that barrel across dozens of pixels are the classic muon signature. If you want to nudge the odds, stack the deck toward darkness, cover the lens completely to block stray light, disable the screen or turn brightness down so leaks don't contaminate the sensor, and give the app permission to integrate for minutes to hours while the phone sits still so motion artifacts don't draw false fireworks. Raise sensitivity, high ISO, long exposure, to help the chip register modest charge deposits, but not so far that thermal snow drowns the rare tracks. Cool phones tend to show cleaner frames, which is why astrophotographers chill their cameras, and why a phone that's been gaming will make a worse detector until it calms down. If you're curious about place, take the experiment on the road. Upstairs and downstairs won't change much, because muons laugh at roofs, but a deep basement, a cave tour, or the thick concrete of an underground garage will trim your rate because the longest tracks get absorbed. A high elevation hike or a ski lodge will boost your catch because the atmosphere above you is thinner. And if it's permitted to run a logging app in airplane mode during a flight, you'll find hits multiply dramatically at cruising altitude where the shower is fresher. An audible illustration of why pilots and frequent flyers tally slightly higher radiation doses over a career. None of this is dangerous to you or your phone at these levels. Space has rained particles on life since life began, and the occasional hit that flips a bit in memory, engineers call it a single event upset, is precisely why spacecraft and safety critical systems use error-correcting codes. In fact, the same sensitivity that lets your phone catch a muon is why big server farms guard their RAM, why satellites reboot gracefully, and why avionics are designed with margins when they fly through polar routes during solar storms. If you're skeptical that a consumer sensor can do real science, you're in good company. Then look at what happens when many phones listen together. A single device is a tiny net, but a synchronized crowd can become a decent mesh. Projects have asked volunteers to run apps that timestamp and geotag candidate events, then look for near-simultaneous hits across neighborhoods to spot extensive air showers. Success demands careful filtering to weed out hot pixels and light leaks, good calibration to align clocks and map each sensor's geometry, and a healthy respect for false positives. Yet the principle works. And when bursts from the sun or rarer high-energy showers sweep through, a widely distributed network becomes a cheap, flexible antenna for the sky. The data are not as crisp as what a tiled array of scintillators with precise photomultipliers would deliver, but for an after-dinner lesson in how science scales, your living room contributes honestly. To keep the exercise clean, treat it like a mini experiment. Take dark frames before each session to mark hot pixels, mask them in software, and count only the surprises. Note the time, location, and a rough temperature so you can see how conditions push the noise around. Try the camera's front and back sensors. Different sizes and shielding make different catches. Test different lengths of black tape and cover the flash. Repeat the session across several nights to prove to yourself that the cosmos is patient but reliable. If you're good with code, a simple script can scan video frames for saturated clusters above a threshold and sketch their bounding boxes. you'll quickly learn that long, straight streaks with steady brightness are rare and precious, while little flowers of pixels clustered in a circle are your local radioactivity murmuring. When you snag a pretty track, zoom way in, you may notice that a biofilter's color mosaic gives the streak a subtle crosshatch as charge spreads across differently filtered subpixels, a reminder that you're looking down into the chip's engineering as well as up into the sky. Don't be surprised when quiet nights still yield nothing for long stretches. 1 per square centimeter per minute is a global average, and your sensor's area, acceptance angle, and shielding conspire to make events sporadic. Patience is part of the fun, just as it is at a professional observatory waiting out clouds. The larger story that frames your little streaks is worth holding. Victor Hess rode a balloon into the sky a century ago and discovered that radiation increased with altitude, proving that a share of it comes from above. Since then, arrays from mountaintops to deserts have read air showers and traced them back to supernova remnants, active galaxies, and other engines that fling particles to absurd energies. Your phone rides on the same principle. A bit of silicon, biased and weighting, registers a charge deposit and turns it into a dot. Stack dots from many devices, and you can follow the weather of cosmic rays across a city. Compare nights near solar maximum and minimum, and you'll learn how the sun's mood modulates the hail. The dose you collect from participating is trivial compared to a dental X-ray or a cross-country flight, and the payoff is real literacy. The next time a headline mentions a solar storm or a radiation spike, you'll have a sensor's eye for scale and a memory of how muons leave lines without asking permission. There's also a quieter habit of mind this experiment can teach. We're used to treating cameras as eyes for color and detail. This one asks you to treat a camera as a counter for invisible events, as a device that registers what the world is doing even when you block the view. That shift from picture to evidence sharpens how you look at gear and claims. It makes you ask about thresholds, noise, controls, and calibration. It helps you separate what's striking on the screen from what's true in the signal. And unexpectedly, it gives you a different affection for the night. When your phone chirps and a streak appears on what should be a black frame, you've caught a traveler that began as violence in a distant object. Punched the sky into a rain of seconds, and then, by luck and silicon, wrote a brief autograph across your sensor. You'll delete the file and go on with your evening, but the knowledge lingers. The high atmosphere is a constant drum. The ground is porous to messages from above. And in the palm of your hand, you hold a device that, between photos of friends and meals, can, if you ask it, listen to the universe tapping. The coldest place humans made is colder than space. Try holding this thought without rushing it. The coldest place humans have ever made isn't a cave in Antarctica or a shadowed crater on the moon. It's a tiny pocket of matter inside a laboratory, chilled so deeply that it falls far below the 2.7 Kelvin glow of intergalactic space, lower even than the Boomerang Nebula's eerie 1 Kelvin chill. And it gets there not by breaking nature's rules, but by using them with patience and precision. Space is cold because it bathes everything in a faint rain of microwave light left over from the early universe. If you expose a lonely object to that bath, it will eventually come to rest at roughly that temperature. But temperature isn't a property of the void. It's a measure of how much random motion and disorder a thing carries. And motion can be coaxed away if you're clever about where the heat goes. A modern low-temperature lab builds a fortress against the world's warmth. Pumps peel away almost all gas, so there's nothing to carry heat by collisions. Shiny shields and nested cans reflect and absorb stray radiation, and quiet refrigerators move entropy step by step from the sample to the room. For solid devices, think superconducting circuits or ultra-sensitive detectors, engineers use dilution refrigerators that exploit the odd quantum chemistry of helium-3, mixed with helium-4. Below a couple of Kelvin, the mixture separates into 2 layers, and forcing helium-3 atoms to dissolve across that boundary soaks up heat, like melting ice absorbs energy from a drink. With repeated stages and careful insulation, you reach millikelvin, then tens of millikelvin, a regime where thermal noise softens enough that a single microwave photon matters and a delicate quantum bit can hold its state longer. Push further, and a different trick takes over. Adiabatic demagnetization. Magnetize a salt or a metal strongly, so the little compass needles inside line up, and the system loses entropy to the environment. Isolate it, then gently relax the magnetic field so those spins spread their order into the rest of the material. Cooling it. Microkelvin temperatures are possible this way, and with nuclear spins acting as the refrigerant, even lower. For loose clouds of atoms, the route to colder than space looks different, and if anything, more elegant. You start by sifting out motion with light, using laser beams tuned so that atoms only absorb a photon when they're moving the wrong way. Each absorption gives a tiny backward kick, and after many thousands of cycles, the frantic thermal jitter quiets to the nanokelvin range. Then you trade numbers for calm with evaporative cooling. Hold the atoms in a magnetic or optical bowl and lower the rim so the fastest ones escape. The ones left behind reshare energy and settle at a lower temperature. When gravity gets in the way, free-falling atoms don't linger in view long enough. You cheat with microgravity aboard the International Space Station or in drop towers and tall fountains on Earth. Clouds can expand in near weightlessness and be delta-kick cooled, their residual drift trimmed with a swift pulse so their temperature tumbles toward the picokelvin frontier. Reports of tens of picokelvin, trillionths of a Kelvin, have been achieved for brief moments in carefully prepared atomic samples. By that point, an atom's speed is so small that a drifting grain of dust would pass it like a speeding car. If this sounds like a loophole in the cosmic speed limit for cold, it isn't. It's a reminder that space is 2.7 K, describes the radiation bath. Not a hard floor on what a well-shielded, actively cooled system can reach. You are always paying a bill. Pumps hum, fields change, lasers fire, helium circulates. Refrigerators don't erase heat so much as export it, moving disorder out of a small system into a bigger one. And there is a true stop sign you can't run. Absolute zero is unreachable. As you approach it, every remaining trick cools less effectively. Quantum zero-point motion remains. The third law of thermodynamics keeps the last bit of disorder out of your reach. Yet stopping just short is more than enough to change what matter is willing to do. At millikelvin, resistance in the right metals collapses and currents flow without loss. Tiny calorimeters become so quiet they can count the heat from single particles. Axion and dark matter searchers lean on frozen amplifiers to listen for whispers that would otherwise drown in hiss. At microkelvin and below, a gas of atoms turns into a Bose-Einstein condensate, a coherent matter wave that sloshes like a single thing. At similar scales, fermionic atoms pair up into superfluids with no viscosity. Ultra-cold molecules collide so gently that chemistry becomes a tidy set of quantum pathways you can switch with a field. In spaceborne cold atom labs, the near-perfect stillness lets atom interferometers drift for seconds rather than milliseconds, sharpening their readout of gravity and acceleration, and hinting at navigation systems that don't need satellites. Even astrophysics benefits from the opposite end of the thermometer. Cooling microwave detectors to the edge of nothing makes it possible to map the faint polarization of the cosmic background and to weigh the sky's oldest ripples. Honesty keeps this wonder grounded. The chamber walls can be room temperature, while the atoms inside are colder than the cosmic background, because vacuum cuts off contact. The atoms are cold in their motion, not necessarily in their internal vibrations. Colder than space exists for milliseconds or minutes in tiny volumes the size of a pinhead, not in city parks. And every degree you shave off inside adds heat outside. No violation, just bookkeeping. But if you zoom out from the plumbing to the picture, there's a thought worth keeping. With enough care, you can create a stillness deeper than the universe's default, and that stillness reveals behaviors that everyday heat hides. It's a style of knowledge that rewards patience over spectacle. Layers of shielding, the hush of vacuum, the slow tuning of fields, and it offers a quiet metaphor you can use beyond physics. When the world's background noise sets a limit on what you can hear, sometimes the way forward is not to shout louder, but to carve out a colder place where the signal can speak. So the next time you step outside and feel the night's thin chill, remember that on a lab bench somewhere, a cloud the size of a grain of sand is colder than the sky itself, drowsing at a temperature where atoms forget how to hurry. And that inside that pocket of near nothing, we learn how matter behaves when almost every distraction has been turned down. One careful degree at a time. Black holes can ring like bells. Lean into a stranger kind of music. When two black holes collide or when a lone one is struck by a passing disturbance, space-time itself thrums and fades in a pattern so orderly that physicists call it a ring down. as if an invisible bell had been struck and now sings its last notes. And if you listen through a gravitational wave detector, what you hear in that dying song is not poetry, but parameters, the mass and spin of a horizon measured by tone and by decay. A pure physics lullaby that ebbs exactly as general relativity says it should. The image works because the mechanism is real. A black hole isn't a hard shell, but a region of spacetime with a one-way surface. Around it sits a kind of echo chamber, set by gravity's geometry, with a narrow girdle near the photon sphere, where light can orbit in precarious loops. When a merger splashes that geometry, two horizons coalescing, or a star tearing nearby, or even a small bump of infalling matter, the disturbance is trapped for a moment between the steep gravitational well and the open sky. Part of the energy falls inward, swallowed without complaint. Part leaks outward as ripples in space-time. What remains sloshes for a few cycles in a handful of preferred patterns. Those patterns are the quasi-normal modes, not normal because they don't last, not abnormal because their shapes and frequencies are as dependable as any Bell's partials. Each mode is a damped oscillation whose pitch and decay rate are fixed entirely by the black hole's mass and spin, and, in esoteric cases, its electric charge. Nothing in the ring remembers what made the strike. That forgetfulness is the sonic face of the no-hair idea. Aside from a few global tags, a settled black hole carries no distinctive features about its past. You can picture it without equations. Strike a wine glass, and the note you hear depends on its size and thickness. Strike a bronze bell, and the overtones tell you what alloy and shape it carries. A black hole's ringdown is the same kind of identification, but the tuning fork is space-time. Heavier holes ring slower, lighter ones quicker. Fast spin shifts the tones and stretches their fade. Higher order modes add brief harmonics that wink in and out as the geometry relaxes. The reason the song dies is as honest as the reason a struck drum falls silent. Energy is escaping. For a black hole, the leakage happens in two directions at once. Some of the wave train flees to infinity. Some slides irretrievably through the horizon, so the modes are quasi, not eternal. Their lifetimes measured in handfuls of cycles for stellar mass remnants, and in longer stately swells for giants. When the first binary black hole signal rolled across Earth, instruments heard the crescendo of the inspiral, the crash of merger, and then, right at the end, a short ringdown whose pitch and damping matched a single smooth horizon. Since then, catalogues have filled with more events. Analysts routinely fit a template to the tail and read off a mass and spin that agree with what the earlier part of the signal predicted through independent physics. That consistency is a test wrapped in a melody. If a remnant's ring were off-key, it would hint that the horizon wasn't the clean Kerr solution Einstein's equations demand. Push the signal to noise high enough, and you can even attempt black hole spectroscopy, disentangling more than one mode the way your ear separates a chord. Measure two or more tones, and you over-constrain the problem, testing whether a single mass and spin explain all of them at once. So far, within uncertainties, the cosmos has played in tune. The mathematics behind this isn't mystical, it's boundary conditions. In the equations for small disturbances on a curved background, you ask for waves that are purely outgoing far away and purely ingoing at the horizon. Then you solve for the complex frequencies that satisfy both demands. The real part of each solution is the oscillation's pitch. The imaginary part sets the rate at which it damps. Because the photon sphere acts like a ridge that briefly traps radiation, geometric optics even gives a rough rule of thumb. In a certain limit, the main ringdown tone tracks the frequency at which light skims those unstable orbits, and the damping mirrors how quickly that orbit lets go. The details are richer. Modes come labeled by angular pattern and by overtone number, and fast rotation splits and shifts them. But the upshot is the same. A struck hole sings a simple family of songs. None of this means every supposed feature is settled. Claims of late-time echoes, faint repeats that would hint at exotic, horizonless objects in place of true black holes, have flickered in and out of the literature. The jury remains cautious because noise and analysis choices can mimic ghostly structure in tales that are, by their nature, near the edge of detectability. Future instruments will help. Space-based detectors will tune their ears to the slow baritones of supermassive black holes, where ringdowns can last long enough and loud enough to separate harmonics cleanly. Improved ground arrays will hear more stellar events, giving statisticians the large samples they need to chase subtle deviations. With better data, the same idea branches into new tests. Do the tones evolve with time exactly as a settling Kerr geometry predicts? Do different lines of sight hear the same mass and spin? Does the ring down agree with the remnant's kick and recoil measured from the earlier waveform? Every yes hardens our trust. Any firm no would point toward new gravity, new structures at the edge, or new states of ultra-dense matter masquerading as holes. It's easy to forget how compactly practical this all is. Engineers who build the detectors tame thermal noise, so a passing ring can lift mirror positions by less than the width of a proton and still be found. Data pipelines wring the last bit of information from a few cycles at the end of a seconds-long chirp. Parameter estimation codes cross-check the in-spiral's story against the ring-down's coda. From all that craft, you gain numbers you can carry, the mass of a remnant across a tenfold range, the spin that tells you how much angular momentum was born in the crash, the confidence that the space-time outside an event horizon behaves under stress, like the textbook geometry you learned to spell. For you, the non-specialist, there is a way to hold this that ties the physics back to intuition without stealing its power. The universe is not silent. When two invisible wells of gravity meet and merge, they jolt the fabric that holds everything, and that fabric rings in patterns as distinctive as any instrument you've known. Unlike a bell in air, the ringing here doesn't carry sound. It carries a change in distance itself, a breath that passes through you without your noticing, except through machines built to notice for you. Yet the human response can be the same. You can listen, identify, and learn. You can accept that after violence comes settling, and that the settling is honest enough to reveal the character beneath the chaos. And when you close your eyes on a night when detectors are awake and the sky is quiet, you can imagine a far-off collision flicker and fade, and know that somewhere deep in the data there is a handful of damped cycles, clean, brief, compliant with a few numbers, that tell a simple, consoling truth. Even in the most extreme places we can name, disturbance gives way to order. And the last note a black hole plays is not a scream, but a tone that says, in the language of curves and time, I am what I am, mass, spin, and nothing else. Earth's core spins at its own pace. Stand on solid ground and picture far beneath your feet, a metal world inside our world. A glowing sphere of iron and nickel the size of the moon floating in a sea of molten metal. And then let a stranger idea land. That inner sphere spins at its own pace, sometimes a touch ahead of the rock you stand on, sometimes a touch behind, nudged by deep forces you'll never feel yet measurable, in the way earthquakes whisper through the planet. Earth is not a single rigid top. It's a set of nested rotors with couplings between them, and the innermost one has its own rhythm. Start with the layout. Beneath your crust and stone mantle lies the outer core, a shell of liquid iron alloy thousands of kilometers thick. In its center sits the solid inner core, a ball roughly 2,400 kilometers across, hot as a star's surface and squeezed solid by pressure. The liquid outer core convects like a slow metal storm, and that motion sustains Earth's magnetic field. The inner core is embedded in this electrically conducting ocean, and magnetism is one of the leashes on its spin. Currents in the outer core drag magnetic field lines. Those lines thread the inner core like taut cords, and electromagnetic torques try to make the solid center keep pace with the flow outside. Gravity adds another leash. Small lumps and bumps at the boundary between inner and outer core, and at the base of the mantle above, raise tiny gravitational tugs that can speed or break the inner core. In between those tugs and torques, the inner core finds its compromise. And the compromise is not always exactly the same as the mantle. Seismology is how we found out. Certain earthquake waves dive through the core and re-emerge on the far side of the globe, and the ones that pass the inner sphere take paths and speeds that depend delicately on how iron is arranged and how the inner core is oriented at the moment they transit. By comparing nearly identical earthquakes separated by years, doublets, and by tracking travel times along the same source-receiver pairs across decades, researchers found small but persistent shifts that couldn't be explained by mere noise or instrument drift. The simplest reading was that the inner core was rotating a little faster than the mantle on average, gaining roughly a few tenths of a degree per year, so that over a human lifetime its crystalline structure would drift a degree or two beneath fixed stations on the surface. Later, analyses complicated the picture in the best scientific way. Some data sets fit better if the differential motion speeds up and slows down, with a period of years to decades, And recent studies have even argued that the inner core's lead may have slackened and, for a spell, slipped behind, an oscillation rather than a steady march. These disagreements aren't a failure. They're a sign that we're probing a system where multiple subtle effects overlap. The outer core's flow pattern evolves. The magnetic field shifts. The inner core might not be a perfectly uniform crystal. Its iron appears to be aligned in ways that make waves travel faster north-south than east-west. There may even be an inner core with a different texture. And these features can leave fingerprints that look like changes in spin when you only have a few kinds of waves to read. Still, the core idea survives scrutiny. The deep center is not locked to the shell above. When the inner core runs a little ahead, the tug it exerts through magnetism and gravity can feed angular momentum back to the mantle and crust. When it lags, the tethers pull the other way, and those trades show up as tiny, irregular wiggles in the length of the day that the best clocks and satellite tracking can see. Milliseconds over years, rather than the tidal drifts you may have heard about, a separate, deeper metronome layered under the lunar rhythm. The liquid part of the core is in on the act too. Its flow sculpts the magnetic field, and that field wanders with time. Maps of magnetism measured at Earth's surface show slow drifts and sudden jerks, kinks in the trend that come and go in a few years. Some of those jerks appear to coincide with changes inferred for the core's differential motion, suggesting that the same deep flow that pushes on the inner core also rearranges the magnetic currents. We don't have a grand final model that ties every wiggle together yet, but the pieces rhyme. Variable flows in the outer core, variable torques on the inner core, variable fingerprints at the surface. If you like pictures more than equations, imagine a steel bead suspended in thick syrup. Twist the bowl and the bead tries to keep up, but it has its own inertia and the syrup doesn't pull evenly in all directions. Nudge the bowl this way and that, and the bead's lead and lag will breathe in time with your hands. The Earth is that bowl. The magnetic and gravitational couplings are the syrup, and the bead is the inner core. Except the hands, moving the bowl, are planetary scale heat flow patterns and magnetic forces that change slowly with time. This isn't academic curiosity. Understanding the core's separate cadence helps us forecast the wandering of the magnetic field that guides compasses and shapes the radiation environment satellites endure. It clarifies why the day-length jitter you see on decade scales can't be blamed on tides alone. And it bounds the models used to interpret seismic scans of the deep Earth that feed into hazard assessments. It also reframes what solid ground means. The continents you trust sit on a mantle that creeps. Beneath that creeps a sea of metal. Within that sea spins a planet within a planet. And the whole assembly listens to forces that act through fields rather than through contact. We learned this not with drills. No tool will ever reach that far, but with patience. Arrays of seismometers and a century of earthquakes gave us repeating experiments. Networks of satellites watched Earth's gravity and rotation with exquisite precision. Observatories mapped the magnetic field over land, sea, and space. From those threads, a picture emerges that's simple to state and slow to internalize. Earth's core is not a slave to the shell. It keeps its own time, and by keeping it, feeds back on the world we live on in tiny, steady ways. If you want an image to carry into the evening, take this one. The planet under you is a layered instrument. The crust and mantle are the drumhead you can touch. The liquid outer core is the air in the drum that carries and shapes the sound. The inner core is the mass at the center that can spin a touch faster or slower, changing the overtones you hear if you listen long enough. It doesn't need your attention. It marches on its own. But when you give it a thought, you find a calm order in the motion, a deep engine with its own pacing, sometimes ahead, sometimes behind, always coupled, always whispering its presence into the small variations that our best instruments tease from the day's length and the field's drift. The ground is steady enough for your life, and yet, in the background, a metal heart keeps time, its own time, inside the world. Quantum randomness shows no hidden pattern, flip a perfect, coin in your mind, and you can blame your ignorance for the surprise. If you knew every breeze and muscle twitch, you'd predict the landing, but point a single photon at a half-silvered mirror, and the surprise that follows does not shrink when you learn more. You can calibrate the optics, shield the room, cool the detector, and still the outcomes arrive as an irreducible scatter that, so far, shows no hidden pattern beyond sometimes this, sometimes that. And that stubbornness is the heart of quantum randomness. The modern story begins with a distinction. Classical unpredictability comes from not knowing enough about the starting conditions, while quantum unpredictability seems to come from the way nature answers certain questions, answers that are not decided until the question is asked. For decades, people wondered whether the mystery was just a clever disguise for unseen causes. But a family of experiments called Bell tests put that hope on a diet. They take pairs of particles born together, send them to far apart stations, and ask each station to make a measurement chosen on the fly. If hidden variables carried pre-written answers that respected everyday notions of separation, the correlations between the two stations would fall within strict limits. Repeatedly, with better timing and cleaner hardware, those limits have been broken. When teams closed the loopholes that skeptics pointed to, ensuring that the particles couldn't secretly talk to each other during the test, using fast random choices to set the measurement angles, detecting a high fraction of the pairs, they still saw correlations that refused to fit any story where local hidden rules decide the outcomes in advance. Other groups pushed the choice of measurement settings back in time by using light from distant stars and quasars to flip the switches, making it absurdly hard to argue that some common cause coordinated the whole trick a moment earlier. None of this proves that randomness is metaphysically absolute. There are exotic escape routes like superdeterminism that say everything, including your choice of setting, was fixed from the beginning, but each new test corners that view into a thinner and stranger box. Practically, the lesson is plain. For certain questions asked of tiny systems, the answers behave as if dice are built into reality. That isn't just a philosophical souvenir, it's a working tool. Engineers build quantum random number generators by tapping those tiny coin flips directly. One simple design sends single photons toward a beam splitter and records which detector clicks. Left is 0, right is 1. Another reads the spontaneous phase noise of a laser, tiny fluctuations no classical model has tamed, and turns that analog jitter into bits. Others measure the arrival times of radioactive decays or the vacuum's own electrical hiss through a sensitive diode. Yet raw randomness is messy. Detectors have biases, lenses age, electronics drift. So modern generators wrap the physics in supervision, watching for skew, running batteries of statistical tests, and then feeding the stream into a randomness extractor, a mathematical ringer that squeezes out hidden patterns and leaves a near-perfect sequence that no one can predict better than chance. You can ask reasonably whether we're simply fooling ourselves with fancy coin flips. Here the field has grown bolder. There are device-independent protocols that certify unpredictability without trusting the inner workings of the gadgets. If two stations produce a strong enough Bell-violating correlation, you can prove that their outputs contain a minimum amount of fresh randomness. Even if the devices were built by a mischievous adversary, as long as you enforce the separation and timing rules. There are also randomness expansion and amplification schemes. Start with a small seed of randomness and use entangled measurements to stretch it into a longer, high-quality string with security guarantees rooted in physics rather than in the honesty of the vendor. This matters because modern life hungers for randomness. Encryption keys, secure web sessions, online lotteries, fair audits, scientific simulations all rely on numbers that nobody can predict ahead of you. Your laptop's random is usually a clever algorithm that produces sequences which look random, but are determined by an initial seed. If someone knows or guesses that seed, the magic evaporates. Quantum sources, when properly monitored, provide seeds that resist that kind of detective work. National labs have even set up public randomness beacons that publish fresh quantum-derived bits every minute, so anyone can timestamp commitments or draw lots with a common, unpredictable reference. The claim that no hidden pattern has been found carries responsibilities, and researchers shoulder them with both statistics and humility. They don't simply eyeball the bit stream, they pound it with tests that look for uneven frequencies, suspicious runs, correlations across distances, compressibility, and more. Passing those tests doesn't prove true randomness, but failing them flags a problem. That is why high-quality generators also expose health metrics, detector rates, temperature, optical power, so that a user can detect drift before it taints the numbers. And when an experiment claims a Bell violation, teams publish the raw settings outcomes and timing, so others can check for accidental leaks or subtle biases. The philosophy hovering behind all this is tender but useful. Quantum theory doesn't give you a secret clockwork. It gives you rules for betting on outcomes. When you prepare a state a certain way and ask a specific question, the theory tells you the odds. Place enough bets, and the pattern of wins and losses matches the odds with hypnotic reliability. But the single result, the next click, the next flash, arrives with a shrug that no one has managed to convert into a forecast without paying a price elsewhere. Some interpretations of the theory say that the world branches to accommodate every outcome. Others say the outcome was latent but non-local. Others say the wave function is a book of knowledge, not an object. What the lab forces you to respect is that, whichever story you tell yourself to sleep at night, you cannot harvest a better-than-chance guess for the next bit without breaking one of the constraints that have been tested again and again. There's a human angle you can carry out of the lab. We often assume that uncertainty shrinks with expertise, that with enough measurement and modeling, the world submits. In many arenas that's true. Weather forecasts have improved, engines run cleaner, diagnoses grow sharper, but quantum optics stands in the doorway and reminds you that there are questions whose answers are designed to keep an element of surprise. Rather than depressing, that can be liberating. It means there are secure doors you can lock with keys no spy can copy from a distance. It means there are experiments where your ignorance is not a flaw but a resource. It means that when you switch your metaphor from hidden mechanism to honest lottery, you gain tools that were invisible before. If you want to try the intuition at home without lasers or vacuum chambers, listen to a Geiger counter near a safe, weak source, or, safer still, watch a well-built quantum random number demo online and feel how the stream refuses to develop a melody no matter how long you stare. The lesson is not that the universe is chaotic. It's that at its smallest scales, it is disciplined enough to refuse patterns where none should exist. And when you finish this thought, and the room falls quiet, you can hold a gentler confidence. The next photon through the splitter will choose a side, and you are not meant to know which. The value in that isn't mystery for mystery's sake. It's the rare kind of uncertainty that can be certified, bottled, and used, a clean unpredictability that secures messages, steadies simulations, and keeps the world honest by reminding us that some doors in nature open only when you knock, and never tell you in advance whether they'll swing left or right. Mirror therapy, reflections, that silence phantom pain. Hold a mirror upright on a table so it hides your missing or painful limb. Place your intact limb on the near side and the phantom on the far. Move the intact hand or foot slowly while watching its reflection, and notice how a simple image begins to loosen a knot that drugs and surgeries often can't touch. Mirror therapy uses vision to rewrite a prediction about your body, and when the brain finally sees what it has been expecting to see, two limbs moving in clean symmetry, the pain that grew from mismatch can quiet, sometimes dramatically, sometimes only a little, but often enough to matter in daily life. Phantom limb pain is common after amputation. Most studies put it between about 2/3 and 4/5 of amputees, and it isn't in your head in the dismissive sense. It is in your nervous system in the literal sense, fed by hyperexcitable nerves at the stump, by spinal cord circuits that have become sensitized, and by changes in the brain's maps of touch and movement. After a limb is lost or immobilized, the areas of the primary somatosensory and motor cortices that once represented it don't fall silent. Neighboring representations can invade, and inputs from the face or trunk may start to activate the hand territory. That remapping by itself is not evil. It's the brain being plastic. But when the maps that predict sensation and the signals that actually arrive don't line up, the error signal can be felt as burning, cramping, or twisting in a limb that is no longer there. Mirror therapy attacks that error with the cheapest tool imaginable: honest deception. The mirror creates a coherent stream of visual and proprioceptive information that says, the missing limb is here and moving freely, while the motor command you issue matches what your eyes report back. Synchronous bilateral movements, opening and closing hands, flexing and extending ankles, rotating wrists, are crucial not because the exercise is strenuous, but because timing stitches the senses together. When vision and motor intention cohere, somatosensory maps settle, spinal reflex gain eases, and the urge that something is stuck unclenches. On scans and in magnetoencephalography, Responders to mirror therapy often show quieter overactivity in pain processing regions and more normalized activity in the pericentral sensorimotor strip. In the clinic, the signal is even simpler. Pain scores fall, and the painful spasms or clenched phantom fingers sometimes release during the session. The technique came to prominence in the 1990s through V.S. Ramachandran's simple mirror box, and since then randomized trials and meta-analyses have painted a cautious but encouraging picture. Not a miracle cure, not a universal fix, but a low-risk method that, when practiced daily for 10-20 minutes over weeks, can reduce intensity and frequency of phantom pain episodes for many people, and improve functional use of the residual limb by calming guarding and fear. It doesn't stop at amputation. The same logic, mismatch breeds pain, coherence calms it, has been used in complex regional pain syndrome, where immobilization and altered cortical maps can thicken pain into a constant defense, in post-stroke hemiparesis, where the mirrored limb can help coax movement and attention back to the neglected side, and even in certain orthopedic and neuropathic pains where movement is safe but feels threatening. Therapists often embed mirror work in a broader program called graded motor imagery. First, you practice left-right limb recognition, retraining the brain's orientation map. Then you rehearse imagined movements, priming motor networks without triggering protective reflexes. And only then do you move with the mirror to fuse intention and feedback. This staircase makes it more tolerable for highly sensitized systems. What does a good session look like? Sit comfortably with the mirror's reflective face toward your intact limb and the non-reflective side hiding the painful or missing limb. Align the mirror so the reflection appears where the other limb should be. Start with small, symmetric movements. Open and close, flex and extend. Wave, trace circles, watching the reflection as if it belonged to the hidden side. Breathe slowly, keep pace even, and aim for a sense of ease rather than range. If cramps or stabbing sensations flare, pause, shake out tension, and restart at half speed. Over days, add tasks you miss, turning a key, buttoning, pouring, tapping a rhythm, as long as the movement remains smooth on both sides. Many people notice immediate, if temporary, relief. Sustained change tends to track with regular practice across weeks, which is why home programs with simple checklists often outperform occasional clinic demonstrations. Mechanistically, several roads likely meet at the same destination. One is predictive coding. Your brain constantly forecasts the sensory consequences of a movement. After amputation or prolonged pain, those forecasts may become sticky, predicting strain or paralysis. So every attempt to move confirms the fear. The mirror supplies the missing confirmation that movement is safe, letting the prediction relax. Another is attention capture. In chronic pain, your attentional system is tuned to protect the threatened part. The mirror draws that vigilance into a non-threatening stream, easing learned danger signals. A third lies in body ownership circuits. Illusions like the rubber hand show how vision and touch can claim a limb as mine. Mirror work recruits that same machinery to re-embody the phantom in a controllable, non-painful way. It is also plausible, though not necessary to believe, that mirror neuron networks, which respond to both performing and observing an action, help reinforce motor programs that have fallen out of use. With all that said, honesty matters. Mirror therapy does not work for everyone. The trials vary in quality. Blinding is difficult because sham mirrors still change attention. People with severe stump pain, poorly fitting prosthetics, or coexisting depression may find the pain too loud to concentrate. Some feel worse at first when the image conflicts with their internal model. And if you have visual neglect, severe cognitive impairment, or skin breakdown in the residual limb, you need extra supervision or alternative strategies. Good clinicians manage these edges by keeping sessions short and frequent, tailoring tasks to the person's goals, and coupling mirror work with desensitization, graded exposure to feared movements, prosthetic adjustments, and, when indicated, medications or nerve blocks to quiet peripheral generators. Safety is mostly common sense. Never force the hidden limb. Stop if mirror work triggers dizziness or severe distress. Beware of compensatory overuse or postural strain on the intact side. And fold the therapy into activities that feel meaningful, so practice survives the clinic. The beauty of the method is not simply that it's cheap, but that it teaches a transferable rule. The nervous system is plastic, yet conservative. When it's been injured or frightened, it trusts congruent evidence over argument. Virtual and augmented reality systems push that rule further, projecting controllable limbs where none exist, adding haptic cues, or mapping residual muscle signals to animate a virtual hand. Early studies suggest these digital mirrors can extend benefits for people who struggle with a cardboard box and a piece of glass. You can hold a softer lesson alongside the science without sentimentalizing it. Pain is not a lie. It is a warning signal that sometimes outlives its trigger, and one path back is to rebuild trust between intention and sensation. One gentle movement at a time. A mirror can't regrow nerves or erase grief, but it can show your brain a story it can endorse. When I try to move, something moves. When I open my hand, it opens. When I ask for ease, the world answers in kind. For the person at the kitchen table with a rectangle of glass and 10 quiet minutes, that story is not a metaphor but a method. And when the session ends, when the reflections fade and you set the mirror aside, you carry forward the practical truth the box has been teaching, that some kinds of pain are not conquered by force, but unlearned by evidence, and that a nervous system given the right, repeated signals can let go of a clenched idea and make room, slowly and stubbornly, for a life that moves again. Light can push things. Solar sails are real. Aim a mirror at the sun, and you can feel nothing on your skin. Yet the mirror feels a push, so slight you'd miss it without instruments, so steady that if you make the mirror big and light enough, it becomes an engine. And today that engine has a name and a record of flights. Solar sailing is real, and it works because light, though massless, carries momentum that can be handed off to anything that reflects it. Start with the simplest picture that doesn't lie. Sunlight at Earth's distance pours in with a constant brightness, and each photon in that stream arrives like a tiny tap. Absorb the tap, and you get a nudge. Reflect it, and you get roughly twice the nudge. The way bouncing a ball back gives your hand more kick than simply catching it. Add up those taps over a square meter, and you're in the realm of micronewtons, millions of times weaker than the shove of your fingertip. Yet physics is kind to patience. A large, shiny sail pushing on a very low-mass craft can trade force for time and win, turning a whisper into a journey. A thin, reflective sheet the size of a small apartment, weighing a few kilograms, can generate accelerations of fractions of a millimeter per second squared. That sounds like nothing until you let it run for days and weeks, letting the velocity build without burning a drop of fuel. The art then becomes two things at once. How to build a sail that is both large and feather-light, and how to steer a force that always points away from the sun into the path you actually want. On the first count, engineers turn to films only microns thick, aluminized plastics like Mylar, Kapton, and newer space-rated polymers, and support them with booms that are themselves rolled tapes or composite spars designed to spring outward on command. Wrinkles, tears, and thermal expansion are not annoyances but central problems because a crease can twist the thrust, and a hot-cold cycle can slacken the sheet until it flutters. On the second count, steering borrows a page from ocean sailing. You tack on light. Tilting the sail changes the thrust vector. In clever geometry, diagonal veins at the corners, shifting the center of pressure relative to the center of mass, lets you crank the orbit's size up or down, or change the plane you ride in, by using sunlight the way a sailor uses wind relative to a keel. Get closer to the sun and the pressure strengthens. Back away and it weakens with distance. So one powerful strategy is the sun diver maneuver. Fall inward to a close approach where radiation pressure is fierce. Rotate the sail to catch the maximum push, and turn that burst into a climb toward a far objective. None of this is only on paper. In 2010, a space agency flew a sail named after a Greek messenger god, and proved the concept in deep space, steering with trapped light and cameras that watch tiny liquid crystals flip black to clear as part of a clever attitude system. Less than a decade later, a crowd-funded mission unfurled a sail about the size of a boxing ring in Earth orbit and showed not just that sunlight could keep it aloft, but that daily, disciplined adjustments to the sail angle could raise and lower parts of the orbit as planned. A quiet, public demonstration that momentum from photons can be harnessed with off-the-shelf ingenuity. Both flights taught hard lessons. Deployment is everything, shiny isn't enough, and area-to-mass ratio is your fuel tank. The promise grows when you realize that continuous, gentle thrust does things chemical rockets can't. Rockets are sprinters. They fire, they kick you onto a new path, they fall silent. A sail is a marathoner. It changes your path slowly but always, and that means missions that require long, patient reshaping of orbits, hovering out of a planet's orbital plane to watch pole caps, holding a position off the Sun-Earth line to stare into the polar aurora, spiraling outward to the asteroid belt without refueling, become practical for small budgets. A sail can loiter near the line between Sun and Earth to monitor solar storms earlier, or hang above Earth's poles in a way that would be brutally expensive with fuel. For exploration further out, sails can escort small probes to multiple targets, nudging their orbits into encounters one by one. And because the engine is sunlight itself, the only propellant you carry is structure. There's nothing to run out. Push the idea harder and it enters science fiction's front yard with science's paperwork in hand. Drive the sail, not just with the sun, but with a directed laser from Earth or the moon. And the pressure rises by orders of magnitude. That's the sketch behind proposals to fling gram-scale probes to nearby stars within a human lifetime of acceleration and cruise, which compresses the material challenges into a different shape. Super reflective, thermally robust sails the size of umbrellas, exquisite beam pointing, and gossamer electronics that can ride the shock of a staggeringly bright push. Even if that interstellar dream takes time, nearer-term laser boosts could help sails climb out of Earth orbit faster or break incoming craft without tanks of propellant, by aiming power where and when it's needed. Honest enthusiasm requires acknowledging the edges. Sails don't work well in deep shade or far from the sun without enormous area. They are sensitive to dust, charging, and micrometeoroids. They test the patience of operators because the feedback loop is slow, and they benefit from navigation support that can measure tiny accelerations and adjust the attitude accordingly. Materials age, coatings darken, booms can warp. The very reflective films that make the engine work also make thermal control tricky as the craft passes from full sunlight to eclipse. But each of those edges is an engineering frontier rather than a showstopper, and with every demonstration, the community learns where to sand and where to reinforce. There's also a quiet cultural lesson tucked inside the physics. For a century, we've told space stories in the language of explosive fuel and short bursts of glory. Sails rewrite that story in the language of patience, surface area, and alignment. They reward designs that are wide rather than heavy, controls that are rhythmic rather than impulsive, goals that accept weeks of steady work over minutes of brute force. If you're a builder or a student, this can reshape your instincts. Sometimes you don't need more power, you need more surface and a better angle. Sometimes the environment provides the energy if you design to catch it. And if you're simply a curious mind watching from Earth, there's a deeper way to hold the idea. Light is not just what lets you see. It is a breath that can move things, very softly, very surely, across millions of kilometers. A constant river you can step into with a mirror spread thin as a dragonfly's wing. Think of a sail opening like a silver flower in the black garden of orbit, feeling for pressure in a place with no air, and then, almost imperceptibly at first, beginning to drift in a direction chosen not by fire, but by the angle of a sheet to a star. That's the kind of propulsion that teaches more than mechanics. It teaches a posture. Catch what's already there, hold it well, and let persistence do what force cannot. When you close your eyes tonight, picture a square of light held taut, turning its face to a sun it will never touch. And remember that motion can come not only from pushes you feel, but from patience you cultivate, out there and, if you choose, in the quieter engineering of your own plans. A teaspoon of neutron-star weighs a mountain. Imagine tipping a teaspoon into the heart of a dead star and lifting it toward the light. If you could somehow keep it from exploding, that tiny scoop would carry the mass of a mountain in your hand. A neutron star is what's left after a massive sun exhausts its fuel, its core collapses, and matter is crushed to densities that sound like fiction, but are measured across the sky. The whole star may pack more mass than our sun into a sphere roughly the width of a city, and inside that pressure cooker, atoms are squeezed past their usual limits so that protons and electrons marry into neutrons. That is why the spoonful is so heavy. Not because neutrons are exotic, but because gravity has forced ordinary matter into a configuration where almost every gap is gone, like a library whose books have been pressed until the shelves vanish and page touches page. If you want a mental yardstick, imagine your teaspoon holding about 1 billion tons, close to the mass of a cubic kilometer of ocean water, or hundreds of great pyramids stacked into a thimble's space. But that comparison is only a doorway. The real wonder is how nature built such a thing. When the iron heart of a large star collapses, inward falling layers slam to a halt on a core that suddenly becomes as stiff as nuclear matter, and a shock, plus a wind of ghost-like neutrinos, flings the outer layers into space. That is the supernova you've seen in photos. The remnant left behind is the neutron-star, its surface a crust just a kilometer or two thick where atomic nuclei still cling together in a sea of electrons, beneath which the rules change again. Neutrons seep out, drip, and swim through a lattice so dense that it may organize into whimsical shapes nicknamed pasta, spaghetti-like strands and lasagna-like sheets formed by the quiet tug-of-war between nuclear attraction and electric repulsion. Deeper still, most physicists think the neutrons become a superfluid, able to flow without friction, and a fraction of protons form a superconductor that locks in magnetic fields of terrifying strength. In some neutron stars, those fields are so intense that we give them a special name, magnetars, and their sudden crust quakes can light up space with bursts of high-energy radiation in less than the time it takes you to blink. If your instinct is to ask, could I ever hold that teaspoon? The honest answer nudges you toward what matters. Remove neutron star matter from its crushing gravity, and it won't stay that dense. The same neutrons that were stabilized by pressure would try to expand. Many would decay back into protons and electrons, and the sample would flash outward with catastrophic violence. So the teaspoon thought experiment is a lesson about context. The weight you're picturing is only meaningful within the embrace of the star's gravity, a reminder that matter isn't just what it is, it's also where it is. And the where of a neutron star is extreme in other ways you can grasp without equations. Its surface gravity is so strong that if you could stand on it, which you cannot, your feet would be anchored with a pull hundreds of billions of times stronger than on Earth. The escape speed from that surface is nearly half the speed of light, so anything that leaves must be launched like a bullet from the deepest well the universe allows before the well becomes a black hole. Some neutron stars spin hundreds of times each second, and if their magnetic field is angled just so, beams of radiation sweep through space like lighthouse beams. We call those pulsars, and their ticks are so steady that astronomers use them as cosmic clocks to test physics and map the galaxy. Others collide in pairs, spiraling together until they merge with a shudder that shakes space-time itself. We've heard those mergers as ripples detected by gravitational wave observatories, and watched their afterglow as kilonovae, whose light carries the fingerprints of newly forged heavy elements. Gold, platinum, iodine, the stuff in your ring, in your salt, in your body, born in the violence of these tiny suns that died and then met again. So the teaspoon does more than shock your imagination. It points to a chain of origins that runs all the way to you. The path from starlight to spoonful is built from real clues, precise measurements of how pulsar radio pulses slow and glitch, which reveal the superfluid inside, X-ray brightness and pulse shapes that let us estimate a star's size, and thus how tightly matter can be packed before physics breaks, and the way two neutron stars deform each other as they dance, which tells us how stiff their insides are. Each method converges on the same picture. Nature found a way to compress matter to nearly the density of an atomic nucleus, and then to balance it on a knife edge between collapse and explosion. The crust itself might be the strongest material in the universe. Simulations suggest billions of times stronger than steel, capable of holding mountains only centimeters high against that crushing gravity. Even the air above the surface is hardly air at all, more like a film a few centimeters thick of superheated particles and light. If these facts feel like opposites, delicate films and billion-ton teaspoons, it's because the neutron star is an encyclopedia of extremes bound into one object. And the practical mind might ask, what is this good for? Beyond satisfying curiosity, these stars are laboratories that let you test ideas no machine on Earth can reach. They show you how matter behaves when the gap between particles disappears, how magnetism behaves when it can sculpt light, how rotation behaves when friction is not a thing, and vortices in a superfluid pin and unpin, sending a star into sudden hiccups we can measure from halfway across the galaxy. They teach you that solid and fluid are not simple categories, that pressure can rewrite the identity of matter, that the periodic table is a travel diary, not just a list. Most of all, they train a habit of mind. The next time you stir sugar into tea, let the spoon become a scale of wonder instead of weight. Picture the absurdity of 1 billion tons poised on a silver oval, and let that image whisper what science keeps finding. That reality often hides its most important truths behind numbers that look impossible until you understand the story around them. You don't need symbols to carry that home. You need a question. What else in your life looks ordinary because you've only ever seen it at human pressure? The neutron star's teaspoon answers by example. Change the conditions and matter reveals a second self. Out there, in the remnants of exploded suns, gravity and quantum rules collaborate to press the universe's pages together. In here, in your kitchen, the pages are loose and friendly. The contrast is not meant to scare you. It's meant to give you a steadier awe. Somewhere tonight, a lighthouse star is sweeping a beam through dust. The crust beneath it is humming with tension, and your world, soft, open, breathable, rests at a pressure that lets tea be tea and a spoon be light in your fingers. Knowing that, you don't just marvel at a mountain in a teaspoon, you learn to read the conditions that make things what they are. And that is the kind of knowledge that stays when the showy numbers fade.